this year has seemed both sort of incredibly short and endless at the same time. But here we are, and thank you for attending. So I'm going to give an overview of the meeting, sort of what we'll be talking about, as well as some updates on CAM and AMWG activities. First, I need to go over some logistics. Let me start my slideshow in full screen. So this is our code of conduct. I think to a large extent, it's pretty self-evident, self-explanatory. Please be constructive and encouraging and so forth. Thank you. Logistics, as far as asking questions and making comments. We're going to ask you to please use the chat function because we won't be able to monitor the raise hand feature. Also note that there will be discussions after each of the sessions, and you can certainly you can ask your question to be addressed during the discussion if there wasn't time after the talks. Just a note to the presenters, please try to send your presentations to Elizabeth Faircloth, whose email is here, before your scheduled talk in case there are any technical difficulties on your end. We can advance your slides and so forth. Okay, so I'm going to go ahead and start the meeting off with an update on CAM and AMWG activities. I have a lot of slides, as usual, too many. I'll try to talk fast. Here's an outline. I'll quickly show something from Cecile Hanai on our updated website. I'll show a nice new, I think, fairly exciting result that the Paley group has provided us, and on last glacial maximum simulations. And we'll talk about vertical resolution, dicor evaluation, physics developments. I'll spend some time on regional refinement activity because it won't be talked about in the presentations. Except for this, there will be a tutorial on Friday, which you have hopefully received some information on, and then we'll just talk about other future directions, and that'll be it. Okay, Cecile Hanai has done some really nice work on redesigning our AMWG website. It now looks like this. Here is the link to the website, and Cecile wanted me to please emphasize that if anybody in the community has a highlight that you would like included on the website, to please contact her, and we'd be really thrilled to put it on the website. Good. Okay. So as I said, one issue that has come up in, one result of CMIP6 has been that several models, including ours, have kind of have shown a very large equilibrium climate sensitivity. And of course, this is an important result, and we're here and other places, other modeling groups are trying to figure out whether this high sensitivity is correct. Our paleo group has, I think, provided some evidence that it may be overdone. What this plot shows is global mean surface temperatures from last glacial maximum simulations. And there will be a talk on this by Zhang Zhu on Wednesday. But the bottom line, the take home here is that the red curve is the last glacial maximum simulation using CSM2 with CAM-6 physics. Proxy estimates for last glacial maximum temperatures are the black line here. And you can see that the red line, CAM-6, CSM2, cools off pretty dramatically, more than the blue curve, which is CSM1, or this orange curve, which is CSM2 with some CAM5 ice nucleation microphysics. In any case, Zhang Zhu will go into this in more detail on Wednesday, and I hope many of you will attend, or all of you, if you can, attend that talk. An activity that we have spent a lot of time on this year is trying to develop a set of vertical grids for a new workhorse version of CSM. This work has been done by a team led by Isla Simpson, who will be giving a talk later this morning. The members of the task team are listed there below. My slides are changing themselves now. I don't know why, but anyway, let's move on. The goals of this vertical resolution effort are to develop a single CMIP class model with a top somewhere around 80 kilometers, with better resolved stratospheric dynamics. We in this task force, and as a result of some input from the community, which we'll talk about in the discussion section, we're also trying to develop a sort of a development version of the model that will be cheaper to run, with a top at around 40 kilometers. Both of these configurations will we intend to have increased PBL resolution. And as I mentioned, Isla Simpson will be giving a talk on this vertical resolution effort later this morning. And there'll be a discussion on vertical resolution after that. Here's some quick summary of some results. As the slide before mentioned, one of the goals here is to try to get a better QBO in the model. And you can see here on the left of the slide that that has been achieved by increasing vertical resolution to about 500 meters and maybe less so to 700 meters. We also, as Isla might discuss, we've realized we probably will need to, just kind of bite the bullet and use different vertical boundary conditions for gravity waves. And here is on the right of the slide is our proposed increased PBL resolution grid. So these topics and more will be covered by Isla in her talk. Another effort that we expect to really get into in a serious way in the coming year is an evaluation of dicores for CAM. As you're all aware, this has been an issue. Well, we've been considering several dicores, including the CAM spectral element dicore, the MPAS dicore developed here at NCAR, as well as NOAA's FV cube dicore. We have decided that, given what I think was the good progress and successful work by the vertical resolution task team, we're forming another internal task team, and you'll see some details tomorrow during a discussion on dynamical cores. But we're sort of we're repeating our strategy for vertical resolution in this die-core evaluation process. And as I said, there will be a session on dynamical cores tomorrow, again followed by a discussion. Along with these activities, this past year, there are 3 climate process teams that have spun up here at NCAR. There's a climate process team on momentum transport in our new, well, it's not new anymore. I still think of it as new, but we're investigating momentum transport in club, the boundary layer scheme in the model. The PI is Colin Zarzicki at Penn State. We're also exploring new approaches to boundary layer convective unified parameterization, the EDMF approach. This is an effort, PI here is João Teixeira. Both of these CPTs will be presenting some results later this morning. There's another CPT that is, I think, very interesting, attempting to couple land surface heterogeneity to our atmospheric physics. That's a joint effort with the land surface group here. Yeah, so this is just a sort of to whet your appetite for the CPTs. Chris Cruz here at NCAR has been looking at trying to evaluate errors in momentum transport within CAM by looking at nudging tendencies in CAM. The results here show some results from these nudging studies that try to evaluate whether the model's surface drag is too strong, and Chris will be showing these results in more detail later this morning. Adam Harrington is doing the real work here at NCAR on the club EDMF implementation. We've been working on coupling a new for us mass flux approach. This is following on work that Michael Vitti has already done in CAM, but we're changing. Well, the idea here is that a new sort of plume will be put into the model, a surface-driven plume that's a little different from the sorts of plumes that are currently used in, for example, the Jean-McFarland deep convection scheme. And as I said, Adam and João will be talking about this CPT later this morning, or sorry, in the afternoon. I misspoke. This is, as I mentioned, there's the other, a third CPT that is coupling heterogeneity in the land surface directly to the model by exploiting some of the higher order moments that are present in the club scheme. In addition to the CPTs, this year we're starting to spin up using funding to spin up, sort of enhance our atmospheric model development activity here within NCAR using supplemental NSF funding. We're referring to it as CAM-7 funding, and the targets for this funding are shown here on the right. We're targeting. We're going to target exploiting, or perhaps even conducting large eddy simulations for boundary layer parameterization studies. We're developing simpler models, cloud computing for accessibility of these models, Regional refinement is a big part of this effort, and we have 4 positions that have been filled under this funding already, and I want to alert everyone here that there is an open ladder track scientist position within AMP that will be focused on boundary layer research, and the link to the job posting is here on the slide. And you're also welcome to contact Rich Neal directly if you're interested. Rich has been doing a lot of work jointly with people in M-Cubed and Research Applications Lab and EOL here in, well, you can see the list of collaborators here. This is an internal reinvestment activity that's meant to examine boundary layer processes in the model. So there's the point here is just to kind of give you the flavor, the idea that we are really we're sort of ramping up our efforts in boundary layer processes in a multi-pronged way. Andrew Gettleman is developing a new a new unified microphysics where there's unified ice and snow. There'll be no need, as far as I understand, no need anymore to no need to identify or pre-identify the ice condense phase in the microphysics. There's a Git repository. So this is now this is an independent repository for microphysics that's being pulled into the model, developed independently in some way, and then being pulled into CAM. That's the plan. And you're welcome to contact Andrew and others working on this with questions. Okay, so I just want to spend a little time talking about regional refinement. This has been an active area in the last year, actually longer, but we now have some comp sets for regionally refined grids in the model. There is a CONUS refined grid. CONUS is the continental US, going from a global sort of outer resolution of 100 kilometers to 12 kilometers over CONUS. There's an Arctic and Arctic Greenland ice sheet set of grids that go down to 28 and 14 kilometers. No, I should say CONUS is 14 kilometers. That's really a better description of NE 240. Both of these grids are going to NE 240. There is also two efforts that are kind of in development right now. One is quite far along, the High Mountain Asia refined grid, and you'll see a picture of this in a second. And I just want to point out to those who may not be aware of it now or yet, that there will be a tutorial on generating variable resolution meshes led by Patrick Callahan this Friday from 10 to 11:30 Mountain Time. And we ask you, if you're interested, to please register here at the website provided here, which is also in the agenda. So here's some, I'm going to be running out of time soon, so I'm going to try to speed it up here. Here's some results real quick from some of the work Adam has done on refined grids in connection or in collaboration with the Land Ice Working Group. Here, the top row shows shows a composited view of storms in the Arctic. Here is these are identified by the Tempest Extreme and then composited by Adam, and it shows the composite precipitation for storms in the Arctic from the quarter-degree grid. And what you see is here the black line and the red line are fairly close. The black line is ERA5 reanalysis precip. Red line is the precipitation from the Arctic refined grid. And you can see it's an improvement over the uniform NE30, which is about 100 kilometer precipitation PDFs. So by enhancing the grid here, we are getting a much more realistic, according to the reanalysis precip anyway, representation of the PDF in precipitation in Arctic storms in the summer. The high mountain Asia grid, which goes all the way to 1/16th, is showing very promisingly some growth in Himalayan glaciers, and this is an exciting result. The number of grid cells with growing glaciers is still way too low, but this is a promising development. Patrick Callahan, in collaboration with the South America Affinity Group, which is a part of the water cycle program, which Roy Rasmussen will discuss on Wednesday, has been generating refined meshes over South America. And here you can see some precip plots showing how maybe in some of the refined meshes, precipitation maxima, which are located near the tops of the Andes in the coarse mesh, sort of move downhill as the resolution increases. We have some external collaborations. One is the IHESP project, which is a joint project with Texas A&M and the Qingdao Laboratory for Marine Science, and they're involved in sort of not ultra high, but very high resolution climate simulations using CSM 1.3 at quarter degree and 10th degree pop and sea ice. And here's the status of their simulations at the moment. They've gone very far along. They're producing some very interesting results with this high resolution coupled version of the model. There's also the CSM2 large ensemble, which some of you may be aware of. That is getting close to completion. I'm going to wrap it up now. There are other topics that will be discussed, and naturally, we've incorporated lots of discussion time, and we hope you will all participate actively in the discussions. And I look forward to interacting with you there at the discussions. And here's a list of the discussion sessions that we've planned for this meeting. So immediately today, we'll be discussing vertical resolution model top issues, and then model physics will be discussed later in the afternoon. So with that, I'll stop. And if there are any questions, quick questions, I'll take them. Otherwise, we can move on. So have I stopped sharing?
Yes.
Okay, thank you.
So can I ask a really quick question, Julio?
Sure.
So you were talking about the CMIP7 process, or sorry, the CAM-7 process, which would hypothetically be for some future CMIP potentially. I'm curious if you didn't really talk too much about what the timeline is, at least internally, in terms of developing CAM-7. Do you have any comments on that?
I would say the timeline is the funding is 3 to 5 years. So and the CPT funding is also 3 to 5 years. So I would say that's the timeline for the bulk of the development.
And so maybe I could just really follow up, and maybe this is for discussion later, but has there been a set, so right, we're just still evaluating CAM-6 and where CAM-6 might have deficiency. So is there a set specific priorities of aspects of the atmosphere that are a focus for improvement in CMIP7, or sorry, I keep saying that, in CAM-7, or is there,
Well,
or that related to the things that you kind of brought up about vertical resolution, boundary layer, things like that?
The focus sort of in terms of physical processes would probably be, it's fair to say it's on boundary layer processes. But also, you know, we can't forget about the coupling between boundary layer processes and microphysics. So but the focus is the current focus for this CAM-7. I would characterize it in terms of physics being on those processes, on boundary layer and microphysics. So I think that's where we feel we need to understand what the model is doing and perhaps improve what the model is doing. So it's 10:26. I'm going to suggest that we move on to the presentation by Nick, and anybody with more comments can raise them later this afternoon or this morning, or any of the other discussion sessions that we'll have. So I'll hand it off to Nick now.
Oh, great. You see that all right?
Yeah.
Cool. There we go. Okay. Hi, everyone. Good morning. I'll be giving the State of WACCM talk today. My name is Nick Davis. I'm a joint co-chair with Nick Petitella as the internal co-chairs. Jessica New is the external co-chair, and then we have liaison Mike Mills. So I'm going to talk about a few things today, how we are going to align WACCM with the new NCAR workhorse model and how that's been going. Some of the new best practices we've developed for using WACCM, including some things impacting CMIP6 output. I'll talk a little bit about WACCM chemical and subseasonal forecasts that are operating in real time or near real time. A little bit about some new last millennium simulations, and then touch briefly on some WACCM-X developments before discussing a few future directions and where we're taking the model. So, as it's already been mentioned, there's going to be some discussion and a talk from Isla later in this session, giving you a formal introduction to this new workhorse model. There's a sample of different grid resolutions shown in the different colors on the right, along with the old WACCM 670 layer vertical grid. The idea is to really reformulate the model for greater consistency. And as part of that, we've been looking at how to expand the suite of model configurations that have a self-generating QBO. So this is really a lot of work done by Rolando and others in the group. The upshot is that across a number of these different but relatively high resolution configurations, somewhere around 500 to 700 meters, at 1 degree global resolution, the spectral element model does have a self-generating QBO, and we now also have a self-generating QBO at 2 degree finite volume model. But again, the key constraint is still that you need high vertical resolution on the order of 500 to 700 meters, which comes out to about 110 levels using the current WACCM model lid. And I think that feeds into an effort to try to make these parameterizations more scale aware and more adaptive, so that we don't need to sit down and retune everything so heavily every time we switch to a different die core or a different horizontal or vertical resolution. And I want to point you to especially Joan Alexander's talk on Wednesday morning. She's going to talk about potentially one way to tie, or basically to improve the gravity wave parameterization for the quasi-biennial oscillation. I am just showing the 2 degree FV spontaneous QBO on the bottom left. There is an issue with a dry tape recorder at a higher vertical resolution. I'll get to that in a second. I just wanted to show a plot of the QBO coherence pattern from error interim on the upper left, and then the finite volume model at basically 110 level vertical resolution, and then the SE die core at 500 and 700 meter vertical resolution. So you can get a good self-generating QBO in these different model configurations and in slightly different vertical spacings. But again, it starts to degrade pretty rapidly once you get to higher vertical resolution, or sorry, lower vertical resolution. So at our high vertical resolution of 500 meters, which is currently the 110 level version of the model, the tape recorder is quite dry. So this is showing you the 10 south to 10 north vertical average UTLS water vapor. On the left are standard pre-industrial control simulations. The top is the 110 layer model, and the bottom is the 70 layer model. And the warmer colors here are wetter signals. So you can see that both the dry phase and the wet phase of the tape recorder in the seasonal cycle are especially dry compared to the 70 layer version of the model. One of the fixes that Julio came up with for this was that increased those Zhang-McFarlane attempts, which seems to moisten the wet phase at least relative to the dry phase, although it doesn't do too much to the dry phase. And so I'd say this is still ongoing, but it's something that we're trying to fix because it's a big issue for these high vertical resolution runs. Okay, so this is just a sample of two things we've been looking at that fall under, I would say, best practices for how to use the model and how to use its output. So earlier this year, Marta Avalos discovered that there was negative age of error in some of these CMIP6 historical output. So on the left is showing you age of error averaged over some 20-year chunks from the historical run in CMIP6. And where the color bar saturates to be white, it's actually negative, which obviously doesn't make sense. Rolando's been looking into some of the details here. There's some sensitivity when you initialize age of error to a really long control integration, which was done for this historical simulation. And that's in part because we think that the age of error, while there is a little bit of a sensitivity to the choice of reference level, the use of a flux boundary condition may be leading to this increasing age at the surface in the troposphere and decreasing age throughout the troposphere. And the big issue is that age of error is just not homogenized in the troposphere like you may have thought. So maybe a flux boundary condition, or sorry, maybe a constant volume mixing ratio boundary condition would help fix this age of error issue. But right now, CMIP6 output has been impacted and has since been pulled for age of error. The other thing we've been doing is looking at consistency runs where we nudge WACCM to itself and try to understand where errors in nudging come from. These are, I would call them sort of perfect tests of the nudging method because we're not nudging to a reanalysis. So essentially, there's no question that the model should be able to match its own state. So these curves are showing you on the top row tropospheric and on the bottom row stratospheric ozone and carbon monoxide RMS errors. And the x-axis is how often the meteorology is updated in the nudged model. So the practical limit of 48 times per day is every time step. And then the different curves show you different time scales. And it's not actually linear. At least for tracers, we can tell very clearly that they're reaching a minimum error at a 12 to 24 hour nudging time scale. It's the same thing for clouds. And there's different ways of slicing the error and different ways of basically finding these sensitivities. But the upshot is, at least for WACCM, we think that if you're going to be running nudging, you really want to stick in this sort of 12 to 24 hour window to minimize errors. I should say that should be in ACP maybe within the next month or so if you're interested in reading about it. So now I just want to quickly talk about two different forecast products that WACCM's currently putting out. One of these is the daily chemical forecast, where WACCM is nudged to the GEOS 5 meteorology. And this is, you can get this output, you can look at plots, you can even look at the plots in worldview if you want. If you go to the ACOM website, it's got a lot of different fields you can look at, including region-specific carbon monoxide. It includes near real-time fire and anthropogenic emissions. Long-term archiving is under construction right now. So this isn't new, but I just wanted to advertise it because we also have the CESM2 WACCM 6 subseasonal to seasonal hindcast and forecast project. This is a project led in part by Jager Richter from CGD. This is showing you on the left some forecasts from January 25th for the polar vortex wind speed with the ensemble mean in the thick blue line and the verification in black. And in the upper right is actually the surface ensemble mean forecast compared to verification for January 4th for the month preceding January 4th. Just showing you that the forecasts are actually doing a pretty good job of capturing the observed surface temperature pattern over the last month. So these have been running in near real time since September 2020. The forecasts are initialized every Monday, and they're currently contributing through SubX to the NOAA CPC week 3 to 4 experimental output. So you can actually go online and look at some of these plots. Nick Peditella is going to present more details of this during the Wednesday morning session, especially about the configuration and some of the early results. But this is definitely a project to watch, and if you're interested in output, you can contact Jager Richter, myself, Nick Peditella, and we can give you some more details. Okay, last millennium simulations. So these are simulations of the coupled climate from 850 to 1850. These were run with WACCM 6 with middle atmosphere chemistry on the 2-degree FV grid. There were 3 different simulations in 850 control with constant solar and no eruptions, and then 2 different volcanic eruption database runs. One was PMIP4 and another was Paleostrat. The 850 control did show a small warming drift over 1,000 years, but you can see in these sort of 55-year smooth surface temperature anomalies, some of these volcanic coolings are pronounced for years to decades after the event. You can contact Betty or Esther, Rolando, or Mike if you're interested. And the last thing I want to do is talk about some WACCM-X developments. High resolution finite volume WACCM has now been coupled to the Naval Research Lab ionosphere model and has been used to simulate equatorial irregularities. So that's shown on the right, the model simulation versus NASA Gold satellite observations of the equatorial irregularities. WACCM-X now fully supports CAM-6 physics and 1-degree horizontal resolution. There's been a generic regridding implementation between the geographic and geomagnetic grids for the ionosphere model. And they're now looking at the SE version of the model and assessing the dynamical core and the new regridding scheme. Okay, so I just want to briefly summarize things and sort of point out where we're going in the next year. I can say that we're going to be fully implementing the SE die core in both WACCM and WACCM-X, and working very hard to make sure that as part of that, we are doing everything we can to streamline the process of getting the model tuned up. Part of that is going to be doing experiments with regionally refined domains to understand resolved gravity waves and potentially contribute to a more streamlined gravity wave parameterization. I don't want to say the words scale aware because that's just a buzzword, but that's certainly sort of in the crosshairs. Some of you have probably heard about NWSC3, the new supercomputer. As part of that, we are looking into embracing GPU programming to make effective use of that, because it's going to be such a large part of the hardware in the new supercomputer. And I think, you know, as two of the most expensive and complicated configurations of CSM, WACCM, and WACCM-X, I think we are continuing to make sure that we're trying to strike a balance between increasing complexity and increasing usefulness of the model. Things like WACCM are super hard to run and incredibly hard to analyze. It's sort of getting to the point where when you run the model, you almost feel like you are literally running Earth, and then now you have two Earths to deal with instead of just one. So I think we'll have more to say on this summer, but I think it's going to be really important for us to really focus on usability, especially for the community, at the same time as we are pushing for higher and higher resolution and higher complexity. And with that, I'm happy to take any questions.
So I have one quick question, which is, so you say that you're implementing the SE die core. What's WACCM's stance on the MPAS and FE cubed die cores? Are you also implementing them, or?
I think it's just sort of a who's most ready and who's next in line kind of thing. We don't have a huge, I don't think we have the ability to commit to implementing more than one at a time, probably at this moment. I can't necessarily say more than that, but certainly because CAM has done so much getting SE implemented, that I think right now it's just sort of a linear thing. Like if any of those other die cores become as mature as SE in terms of use, then I think it's just sort of a matter of when, not, you know, if. I don't think there's any resistance to MPAS or anything else.
Okay, thanks.
For sure.
And Peter Lauritsen may have more to say about that tomorrow. The deep versions of these die cores are kind of part of that. They're not optional.
Yeah. Well, if no one has any questions, we can move on.
I don't see any questions in the chat. So.
Okay.
Oh, there's one from Maria.
Oh.
Val Martin. Do you want to?
Yeah, I can. Maria's asking about tracer errors in the model. So I was talking about nudging. It's actually model-to-model comparison, and it's comparing WACCM to itself. So we were actually nudging WACCM to its own free-running simulation. So the only thing that could cause a deviation of the meteorology and the tracers from the free-running simulation we were nudging to is the nudging scheme. So because of that model setup, while it's not necessarily going to be relevant for, you know, nudging to a reanalysis, it means that we can directly ascribe all of the errors in the fields to the nudging itself. Yeah, that's a good question. Thanks.
So it doesn't look like there's anything in the chat right now. Again, you know, discussions are freely, well, there's going to be a lot of them. So if you want to ask something, then go ahead. Anyway, maybe we should just move on now and to Louise's talk.
Okay. Hi, everyone. And thank you all for joining all of us. I'm Louisa Emmons at NCAR, the internal co-chair, along with Xiaohong Liu. And a big thanks go out to Simone and Francis, who answer all your questions and help get all the inputs into the model. So I'm just going to give a brief overview of recent developments and planned developments, and just a very minor, quick results, and also a discussion of Musica. So our CESM 2.2 was released since our last meeting, and it includes a lot of new functionality, not yet scientifically validated features, including spectral element and the CSLAM configuration. So there are comp sets in CAM-chem for these. And in particular, there's a comp set for the regionally refined configuration of SE in CAM-chem that we're calling Musica version 0. And one of the grids has 14 kilometers over CONUS, but we're also starting to create other grids, refined regions over other parts of the globe. And there's several presentations on Thursday morning showing results from these configurations. There are also comp sets for nudging to the observed meteorology on the model levels, as Nick was just talking about a bit. There's a small update to the formulation of secondary organic aerosols, adding the NOx dependence for the BBS scheme. There's also a comp set for the new expanded isoprene and terpene oxidation that Becky Schwantes has implemented and published. And we also have the aerosol convective scavenging. It's in a comp set, the comp sets for CAM-chem. And a lot of this discussion has been presented in previous workshop and working group meetings. So we're working on a number of things for CESM 2.3. There's no date yet for this, but we're working towards these. There are a couple corrected bugs related to the surface area density and the simple SOA scheme in CAM. And there are a number of aerosol related developments that we've been working on for some of them for a number of years, and realized it would really be best to put these all together and then tune the model based on them. So there's the mosaic gas aerosol exchange, which will allow for the simulation of ammonium and nitrate aerosols. There's a new MAM5 scheme that adds an additional course mode for sulfate in the stratosphere, and Ziming will talk about that tomorrow. There's a new dust scheme, brown carbon radiative impacts, and which have been talked about in the past, and Hunter will talk about tomorrow. And the aerosol convective scavenging will be added to CAM and WACCM that was already put into CAM-chem. And we also plan to have comp sets for the online ocean emissions, which are for OVOCs and DMS. And Rafa will tell us on Thursday about the very short-lived halogen chemistry they've been implementing and developing. Some additional things are adding the HEMCO emissions module to handle help us handle emissions into CESM2, calculating photolysis rates online. I've been working on coming up with some simpler chemistry that'll be suitable for climate applications. Of course, we're also still working on more complex chemistry to particularly for anthropogenic and fire-related emissions. We're working on KARMA. Simone is really leading that effort, the sectional aerosol scheme. And then there's several things related to the land model that are important for the atmosphere that we're working on, coupling the fire emissions calculated in CLM to CAM-chem, calculating nitrogen emissions from the soil, connecting them to the atmosphere, and calculating biogenic emissions with Megan version 3. And I'll show some slides on these topics in a second. Another thing I want to make sure everyone understands is has heard about, or you've all probably heard about Musica, the multi-scale infrastructure for chemistry and aerosols, and will really be hoping to be a model independent infrastructure to help simulate aerosols and chemistry at different resolutions. We have a web page. There's a vision paper published in BAMS this fall, led by Gabby Pfister. We're developing an implementation plan that we hope you'll all be, anyone interested is welcome to participate. And we're doing all of this development really in partnership with SEMA, and Andrew Gettleman will tell us quite a bit more about that in the next presentation. And as I said, what we're calling Musica version 0 has been released in CESM 2. So we're really hoping to modularize the different components of the chemistry and aerosol to connect to parameterizations to connect to the physics, and then of course still include all the coupling available in CESM to the other component models. So we have a number of working groups, 7 working groups on these different topics, led by people from NCAR as well as outside university groups and other organizations. And we're currently writing the implementation plan. So please get in touch with us if you're at all interested in being involved. And I'll pass the microphone to Alma, if she's there.
Yes. Hi, everyone. Thanks, Lisa. So I'm Alma Hodzic. I'm also at NCAR. And so I just wanted to say a few words about Musical with an L, which is a community effort that we started with Natalie Mauwald recently to build a generalized aerosol programming interface, API, for use in new or old weather and climate models. And the idea here is really to leverage all the work and effort that ACOM and NCAR is doing on Musica, and to make that available to the larger community. This API, the interface will sit between the host models. We have number of participants and interested models to adopt it, and a library of aerosol models and modules that will be used, and we will enable it to be used by any of these models. So we have already met a few times with a large group of participants from different universities in the US. For now, it's only in the US, and also the labs. And we drafted a white paper, and right now we are writing a proposal. So there is a meeting next week, and if you haven't been already in touch with us and you're interested in participating in joining this effort, please email Natalie or myself, and we can put you in this group, and we can all work on this together. So thanks, Lisa. I'm giving it back to you now.
All right, great. Thanks, Alma. So just to go over a couple of these new developments. Becky Schwantes is working on what we're calling TS3 chemical mechanism, and this is to expand the alkane chemistry from what we currently have, just propane and a big alk, to all these different species, and it'll be evaluated with ATOM, be useful for anthropogenic and fire emission applications. Alex Gunther is developing Megan 3.1 and into CLM5. Actually, his graduate student, Wei Wang, is doing this work. And so it'll expand the biogenic species that are calculated, and also include some drought and environmental stresses. As you can see on the right, isoprene flux on the top, and then to the right, the impact of having drought stress, and then monoterpene fluxes with high temperature and low temperature and high wind stresses that really impact the emissions. So that work is moving forward. And Maria Valmartin from the University of Sheffield has been working on implementing soil, NO, and ammonia schemes that are really connected to the nitrogen cycle in CLM, and then produce emissions that are connected to the atmosphere. And there's bidirectional coupling from then nitrogen deposition from the atmosphere back into the land model. And her results look very good. The total global soil NO emissions are comparable, if perhaps on the slightly lower end of previous estimates. And the agricultural emissions of NO are very similar to other estimates and inventories in these various regions. And group at Boston University, graduate student Anthony Wong with Jeffrey Geddes has taking this initial implementation and building on it, adding the pulsing of emissions after rain and studying the impacts on future climate and land use change, and addressing some questions like comparable and competing climate and land use effects may have effects on reactive soil and soil nitrogen emissions. And we're potentially missing air quality climate penalties by not including these calculations. And finally, we're working on improving the diagnostics and model evaluation infrastructure for Musica, and essentially CAM-chem, trying to develop a simpler way of comparing a variety of atmospheric chemistry observations to the various configurations of CAM-chem, CESM with different grids, and coming up with a set of diagnostics and websites for analysis. So if anyone's interested, please get in touch with me. I'd be happy to have your input and assistance in developing this project. So I'll just end there, and we have web pages and for more information, and we're developing a wiki page for Musica to help people get started in running Musica version 0. Thanks. Are there any questions at the moment?
Apologies if this is too in the weeds, but do you have any plans for being able to run Musica on GPUs? I think we'll hope to take advantage of them. I don't know the details at the moment. We haven't gotten started on that, I think. Okay, thanks.
Musica is essentially at the moment is CESM. So whatever gets developed for CAM, we'll take advantage of.
Gotcha.
So Peter, this is Andrew. I'll just say that we can talk more about it, but we do have plans within CAM and CESM to start moving to GPUs.
Okay.
And Louisa, there are two questions. Well, there's one question about emissions in the chat.
Yeah, I'm not sure what, maybe you can email me and we can discuss that. The emissions currently are very flexible. You can run whatever year you want. We have CMIP emissions from 1750 to 2100. There are plenty of options for emissions. And we're still thinking about the Musica tutorial. Please join Patrick's tutorial on Friday to learn about making a new grid as a start. Anything else?
No, there are no new questions in the chat.
I see Andrew ready.
Yeah.
Pass it off to you.
Okay.
Okay. Can everybody see that?
Yes.
Yeah.
Okay. So good morning, afternoon to some of you, I guess. It's good to, well, not see everybody, but at least see your name. This is going to be a discussion of kind of overarching things on the System for Integrated Modeling of the Atmosphere, or SEMA. And it's an update sort of for all the working groups. SEMA is the idea, it's a framework or an infrastructure, it's a system for building community atmosphere models from the monoscale to the exascale. I'll use that monoscale word as saying we're going from simplified models from single column all the way up to exascale models. This is a project that's starting to involve lots of people outside the institution at NCAR, but is involving people across NCAR as well. Has 4 science co-leads, myself for climate, Bill Skamrock for weather, Mary Barth for chemistry, and Hanli Liu for geospace. So the concept or the vision is that currently NCAR develops and maintains several different community atmospheric modeling systems. Many of these are partially integrated, as we've seen, but they have their own flavors. So for climate, we have CESM that Julio talked about, and CAM. Chemistry, we have WACCM and CAM-chem inside of that Louisa just talked about. For geospace, we have WACCM-X that the NICS just talked about, along with the TIE GCM, which is a separate geospace model that HAO uses in that community. And for weather, we have WRF and MPAS as community models. So we still struggle to work at these interfaces of these systems, and what if we could bring them all together better? And obviously, the large group here has been struggling with this on the first 3 for a long time for climate, chemistry, and geospace. And we've been getting much better at doing that together. We haven't really extended to weather yet. And so this brings together the ability to do some of these really interesting frontier applications: coupled weather prediction, climate extremes, space weather, air pollution, and coupled polar prediction are all important things that we're struggling to do now. We can do it a little bit, sort of generally one-off configurations, but to do it better and more robustly for the community requires a slightly different approach. So that's CEMA. It's this effort to unify our community atmospheric modeling across weather, climate, chemistry, and geospace. This has been developed and defined at NCAR and with the community. The updated CEMA vision results from a community workshop in June 2020 that many of you were at. There's information on the UCAR wiki that has all that documentation and results of the workshop. So this vision it's a configurable system, just like we have different configurations now of CAM, WACCM, WACCM-X. CEMA is designed as a configurable system. It is not a single model. It's an atmospheric model within an Earth system model, within CESM, within that infrastructure, and CEAM. So I'm talking exclusively about the atmosphere, but you'll see implicit in this is that we're running it in a coupled system, those functionality and components are available. It's a minimal set of interoperable components, and the interoperable components inside of the atmosphere are the physical and chemical parameterizations and the dynamical cores. But using common infrastructure and methods, so sharing and extending our diagnostics, teaching tutorials, et cetera, across these different domains, and to reduce the duplication of effort is one important aspect of this. And this really is a community working together towards frontier applications. It's an extension of the community that's listening to me now. So that already crosses weather, climate, and chemistry, and it's a hallmark of CESM, or sorry, climate, chemistry, and geospace. It's a hallmark of CESM that we're actually to that point already. So what does this look like? Well, let's blow up the atmosphere and call it CEMA for the moment. It's basically the infrastructure, expanded infrastructure inside of CESM. We actually use a pointer. So obviously we have a coupler, which is going to be the CMEPS coupler inside of CESM. There's an ocean model, land model, an ice model, all the different component models. If we focus on the atmosphere, let's just blow that up for a minute. And inside of that, there's physics and chemistry and dynamical cores. And so CEMA is this set of interoperable components is what it's envisioned as. And the following slides are examples of how you can actually do this. We have physical and chemical parameterizations. We have different dynamical cores. We have a physics dynamics coupling layer, and we have data simulation. Don't worry exactly about whether the data simulation is inside the atmosphere model or around the coupled system for the moment, but it's just illustrative. So CAM-7 that Julio described the development of might look something very much like this. It would have the Musica aerosols, which are essentially the future version of the MAM aerosol package that we're using right now, along with CAM physics, which would be evolving along the usual trajectory. And just for illustration purposes, I've put down the SE dynamical core. Obviously, as Julio said, and as Peter will talk about tomorrow, there is going to be a dynamical core selection process for CAM-7. But there's also different configurations. So for example, there is now a polar configuration of CESM that CEMA has helped develop that uses the regional refined version of that down to like 14-kilometer resolution over Greenland, and soon we'll have versions over the Antarctic, and soon will be coupled. So there's different polar versions that are focusing on a regional refinement version of this. There is also a chemistry version, which has regional refinement. This is sort of Musica version 0 that adds the full tropospheric and stratospheric aerosol sets that are from CAM-chem and from WACCM into this model. And that might also run with a higher top. And then we have a geospace model, which and essentially is WACCM-X. And this has the plasmasphere and thermospheric physics that Nick talked about, along with the CAM physics, using the SE die-core. And in this case, for example, you would be using initialization or data simulation to actually simulate a particular space weather event, which is also something that Nick showed. Now, finally, CEMA would also have a weather configuration. So this, for example, might also use a data simulation or initialized framework. It might have physics that looks more like WRF, or it may be an adaptation of WRF and CAM physics, and it would likely or would use the MPAS dynamical core, which is a non-hydrostatic dynamical core appropriate for weather scale resolutions. Still a global model, however. So all those things are sort of possible for CEMA. What's the status of this? Well, we started as a small reinvestment project last year, last fiscal year. That was CEMA V0. We developed these polar configurations. We did some work on the spectral element dynamical core, and also worked on the CAM-SE regional refined configurations with chemistry. There was this community workshop this past summer, and there's an updated vision document that led us to launch and adjust for CEMA version V1. So that's a current reinvestment project that started a few months ago. This is targeting more ambitious configurations across these CEMA frontiers. And we brought in a software engineering project manager at a quarter time. That's Jordan Powers, who's worked on M-Cubed and is also responsible for the Arctic predictions, or the Antarctic prediction system, AMPS, works in M-Cubed. So one of the other aspects of CEMA is that we're leveraging lots of other efforts. We're leveraging support for field projects, doing, these are actually 2 field projects in East Asia. ACLIP is a chemistry project. PRECIP is looking at storm dynamics and tropical cyclones, looking at configurations for that, which I'll show in a minute. Also looking at high resolution and exascale configurations. These are Earthworks and IHESP. Julio briefly talked about IHESP. I'll talk about Earthworks in a minute. And we're also then bringing in, along with these projects and others, we're bringing in outside collaborators for this. The goal of CEMA V1 right now is we are aiming to release a series of configurations as CESM comp sets in the summer, fall of 2021. These will be atmospheres that basically are advances on what we have now, along the lines of some of the configurations I just showed schematically, that inside of the configuration, it will just say CEMA inside of the CESM comp set. And we are standing back up a major communication effort, both internal to NCAR and CESM, and also external within the CESM and other modeling communities. So some specifics of what these applications actually are. As I said, the goal is that sometime in the summer, we're actually going to be releasing these as comp sets that people can run. And I've highlighted in yellow sort of all the ones that are typical advances on configurations for CESM, but you see we're actually pushing the envelope in a lot of different directions here. So won't talk too much about a coupled weather prediction model, but that's going to be a 3-kilometer finest mesh in a global configuration over East Asia with a coupled ocean. That would be initialized. That would be for the PRECIP field project. A similar configuration over East Asia would be for ACLIP, but that's with adding chemistry to that 3-kilometer refined mesh. Both those would likely be with the MPAS 9 hydrostatic dynamical core. For climate, we're focusing on hydrological climate extremes, and that's a couple of different refined mesh configurations. One is looking at a refined mesh over the United States, which would get down probably to about 15 kilometers. Another one over South America, which could be, right now it's envisioned that that's the mesh that Julio showed that Patrick Callahan is working on with that South American affinity group, and that's actually hydrostatic. It could also be non-hydrostatic. We're also looking at a globally uniform 4-kilometer CAM MPAS. This is the preliminary version of what's the Earthworks configuration. Earthworks is a project funded by NSF to help develop this, that's being led by CSU, by Dave Randall and Jim Hurl, that has significant NCAR involvement, both with myself and Bill Skammerock in M-Cubed, and also with Sizzle doing computational work. And this is actually, as mentioned in the earlier comment to Peter Caldwell, this version of CESM, starting with the atmosphere CAM, using the MPAS dynamical core, we're also doing a significant amount of work to move that onto GPUs. So this will move the whole system eventually in a couple of years onto GPUs. But our goal right now is to release at least a globally uniform CAM-MPAS mesh that we can use for testing. And this is the diamond configuration, essentially. What I've shown is actually synthetic OLR from a 4-kilometer MPAS simulation, which is one of the diamond configurations that Falco Jute produced. We hope to be able, within 6 months or so, to do test versions of this with actually CAM and CESM. That's where we're going. Space weather prediction, the goal is to do what Nick showed with a coupling to the ionosphere with a 25-kilometer SE core, but actually have an interactive ionosphere, not just a one-way coupling. And then I think initially we may be releasing the one-way coupling. And then for polar prediction, this is a nice animated GIF from Adam Harrington that you can see the storms actually refining as they get into that box, which is the high resolution region over the pole. This is a uncoupled version right now, but we're working on a coupled version. I know that Adam and the Polar Group are working really hard on this, and they're making some great progress. A coupled version with Greenland and a coupled ocean, and also looking at Antarctic configuration. So again, this is a whole series of suite of different configurations across CESM and across the different configurations of the atmosphere that we're going to try to release this year. And by release, that means these are going to be functionally supported, not scientific support yet, but people who are interested, please let us know and talk to us, because we can give people also early access to this to help us do development of that. So what is the benefits of CEMA for CESM and CAM? CEMA provides an underlying framework that should be a lot more flexible and should give us a much better foundation for the future. Our goal is to support and extend our existing applications for CAM, WACCM, CAM-chem, also WRF and MPAS. The existing groups, so the AMWG, the polar configurations, polar group, contribute to and define these CEMA goals. And the key here is that CSM determines its own configuration. So the AMWG, the WACCM working group, and the chemistry working group, they select the dynamical core and physical parameterizations that are appropriate to them. We will support multiple configurations. We're aiming at a minimal set, but we're trying to coordinate development as much as we can. But note already that CEMA is supporting multiple dynamical cores in its version 1 configuration, the SE regional refinement, SEC SLAM, and MPAS, for example. And we're also trying to work as much as possible within existing governance structures to make things overlap, to improve communication, so that we're not adding an extra layer of management to the atmosphere. So this extended group already has a lot of work coordinating across the atmosphere, and the goal of CEMA is just to help improve that. So again, we get benefits for CSM, improved robustness of atmospheric models across scales. We intend to get a more complete set of simpler and more complex models. So for example, in the context of this, we'll end up with new workflows. One of those is likely to be that we get an LES configuration. Another one is that we're moving the whole model onto GPUs to do more exascale type configurations. So again, we're going to support diverse configurations for different climate questions. That includes physical and dynamical core options and vertical resolution. To some extent, we're already doing that now across these 3 different working groups. We're sort of taking this, making it better, and adding weather to this picture, which gives us also much better access to prediction. So initialization and assimilation capabilities are coming, and better workflows for that. So improved collaborative science, workflows for things like assimilation, regional coupled modeling even, and large eddy simulation configurations. And again, this is expanding what we do and accelerating it by coordinating our efforts for greater efficiency. And I think we're already seeing better collaboration across the different laboratories. It may not be obvious within the working groups, but along the back end, we've got a project manager that's helping to build CEMA and coordinate across the software engineering of all the different working groups. The 3 here, plus the software engineering working group for CESM across 4 different laboratories. So this also brings more resources and people to develop an atmosphere model and leveraging other communities' expertise. So for example, in the weather field, we're thinking about forecast verification diagnostics and integrating that into CESM to do better, extend some of the work that people have done in the past with CAPT and short-term forecast experiments. So in summary, CEMA is a unification effort across our atmospheric models, our community atmospheric models, to enable frontier science. It extends the CESM infrastructure. I think there's massive benefits to the CAM community, and it's responsive to science needs. So a lot of these configurations have been developed with the CESM working groups. The working groups decide where CEMA should be going. CEMA is headed towards a diverse model, or sorry, CESM is headed towards a diverse model hierarchy. And CEMA is designed to support that, not just on the complex model side, but also on the simpler and more idealized model side. So if you're interested in these configurations, please let me or one of the other co-leads or just the working group co-chairs know. We're in contact quite a bit. And again, that's myself, Mary Barth, Bill Skamrock, and Hanli Liu. And let me see what's in the chat. Let's see, where are we? Is it easy for the?
Go ahead, Andrew.
I'll just read them off if that's
All
easiest. Whoops, let me stop sharing. No, I just lost it. Okay. Is it easier for the user? Oh, sorry, I've got to go all the way back up. Julio's question: what will this look like to the users? A single set of unified scripts for building and running. I think that's the intent. We'll have to see where the workflows go. I think there might be actually multiple scripts because some of the workflows are going to be different. I mean, by the time you get to weather and ensembles, they may look slightly different, but it's going to be the same underlying CESM infrastructure. So hopefully the scripts will be a series of things that are much more coherent for people. And they're going to be suggestive scripts because we're going to be using essentially the same infrastructure that most of us are familiar with. So Adam, hopefully we just lost Adam and not me. Hopefully Adam's back. Is it easy for the user to create their own model input initialization using refined mesh of the interested domain? That's one of the things we're trying to get better. I think if you come to the workshop on Friday for refined meshes, that is getting easier. One of the big things I would say that CEMA is working on now is a unified online regridding infrastructure that will vastly facilitate the ability to work with unstructured grids and regional refinement, because you won't have to deal with all the input data. It will just be handled on its own. And then is for climate application of CEMA v1, Earthworks, is it also a coupled model? Yes, not for CEMA v1, we're not focusing on coupled, but the Earthworks is a 5-year project and its goal is a coupled version at 4-kilometer resolution. No mention of CCPP in the presentation. What is the current role dependencies of NOAA in CEMA? Basically, we haven't, the CCPP is moving along in the background. I'm happy to talk more about that, Dan, but it is not critical it's not on the critical path for CEMA v1 to get these configurations out. It is likely we are making significant progress on the CCPP, but we decided to be science forward. And we determined that the CCPP infrastructure wasn't vitally necessary to get to this. I think by the middle of this year, by the time we deliver CEMA v1, we will have a good cut at the CCPP in the infrastructure. And I'm happy to talk more about that. But it's definitely, we propose this as science forward while we take that off the critical path so we don't stress out the software engineers. We also don't upset any of the other science across the working groups. We didn't want to actually force ourselves to integrate the CCPP right now, but it is in process.
So Andrew, we're starting to run over a little bit, so I'm going to suggest that people contact you directly or wait for the discussion session. I think we should move on to Isla's talk, if there she is.
I didn't expect to have that background. Okay.
Okay. Okay, thanks. Yeah, thanks, Andrew. And let's move on. All right.
Okay. You see my slides?
Yeah.
Okay. Right, thanks. So as Julio mentioned, I'm going to give a summary of what we've been doing in getting towards the vertical resolution for the next workhorse version of CESM. So this is work that has involved many individuals that have formed this task team who've been working on this since last spring. So some of the desired features that we wanted with this new vertical resolution, I'll go through here. So I'll show plots like this quite a lot. This is showing on the x-axis, the vertical grid spacing, and on the y-axis is where we're at in terms of the height within the model. So here what you see is WACCM and then CAM. And so we wanted to lower the lowest model level down to somewhere between 10 and 20 meters. It's currently at 52 meters. We wanted to increase the resolution in the boundary layer and increase the resolution in the troposphere and lower stratosphere enough to improve the representation of the QBO. And then the idea is to have an intermediate top somewhere between CAM and WACCM, so high enough to have a reasonable representation of the stratosphere, but low enough to try and limit the computational cost. And then also that has advantages when it comes to initializing seasonal to decadal predictions as well. So we started out with investigating resolution in the free troposphere and lower stratosphere. And the way we started this investigation is to start with the research version of WACCM that Nick mentioned earlier, which is this 110 level WACCM developed by Rolando and Yaga, which has about 500 meter grid spacing in the troposphere and lower stratosphere. And what we did was then to systematically degrade the resolution in 100 meter increments down to 1,000 meters. And we ran AMIP type simulations with specified chemistry with each of these grids. And so we looked at a lot of things and everyone looked at different aspects. And so I don't want you to think we didn't look at a lot of different things, but I'm not going to show most things here because many things didn't really depend on the resolution. And what I'll focus on here are the aspects that did. And these are mostly aspects in the tropical lower stratosphere. So the QBO in particular is one thing which is sensitive to the grid spacing. And so what you see here is time series of zonal mean zonal wind averaged from 5 south to 5 north. And so this is the QBO. And so each of these grids here has a QBO of some form, but you can see that for the lower resolution, it's not really coming down as far into the lower stratosphere. And you can see that a bit more clearly if we just plot a measure of the amplitude of the QBO. So the black line here is year 5. And you can see that the 900 and the 1,000 meter grid spacing have a lower amplitude of the QBO than the higher resolution ones. This is one metric that comes from Rolando, which is thought to be kind of important in our ability to simulate the QBO properly. And so what Rolando does is he composites months when the QBO winds at 60 hectopascals are transitioning from easterly to westerly, and then plots aspects averaged over the tropics. So you see that these composites for different resolutions here. And the black line is showing the zonal mean zonal wind. So at these times you have westerly winds in the lower stratosphere, and they're descending down at this moment. And then in the blue and the red, you see the tendency of the zonal wind. The blue is the tendency from the resolved waves, and the red is the tendency from the gravity waves. And so what you see is the difference here is that in the higher resolution, the blue is positive. So there's a role for the resolved waves in driving that descent of the westerly phase of the QBO. And at the lower resolution, that's not the case. The descent of the QBO is really being gravity wave drag driven. And so this is thought to be an important feature for getting the QBO to extend far enough down into the lower stratosphere. Probably related to this, there were also differences in the representation of wave activity in the tropics. So these are wave number frequency spectra for the anti-symmetric component about the equator. And what's highlighted here in the red circles are the mixed Rossby gravity waves. And you see this systematic dependence on resolution with more wave activity at the higher resolution. And this is not well observationally constrained, as you can see from these two reanalyses. But ERA 5 has a higher resolution underlying model, and it shows more wave activity. So we should probably think that the higher resolution ones are the more correct ones. So for this conclusions of this vertical grid spacing investigation, many things did not show much dependence. Features that did are aspects in the tropics. So the QBO amplitude is improved at higher resolution, and there's more of a role for resolved waves in driving the descending westerly phase of the QBO. There was also more mixed Rossby gravity wave activity. And I didn't show this, but there's some indications that there's slight improvements in the MJO with higher resolution. And of course, there could be unforeseen benefits of enhanced vertical resolution as we go to higher horizontal resolution. So we decided that somewhere kind of between the 500 and the 700 meter grid spacing range was preferable. So we continued to investigate those two resolutions further. And the next thing to do was to lower the model lid height. So we took the 500 and the 700 meter grids, and we just chopped off the model top to 80 kilometers. And we found that we could do that without really much degradation of things in the lower stratosphere. So we still get a QBO in these configurations with the model top chopped off. And at this point, we did some additional tuning for the QBO period. And this is showing the amplitude of the QBO after that tuning. And so both of these have a good period, but you find that the 500 meter grid spacing shows a higher amplitude of the QBO than the 700 meter grid spacing. So then we asked, well, can we limit the computational cost a bit by tapering off the resolution in the upper part of the model? And so we did this with the 500 meter grid spacing. So at this point, if all we did was chop the lid off, we'd be looking at a 92 level model, but we hadn't touched the boundary layer at this point. And the expectation is that would add in another 10. So we'd be looking at a 102 level model with this. So we tried a few different tapering options. So one starting at 25 kilometers, and then one tapering off at 20, and then one at 15. And it turns out that this does have a degrading effect on the simulation for the lower tapers. So if we taper off too low, like in the 15 and 20 kilometer case, it really messes with the QBO and we lose the amplitude of the QBO in those cases. But the 25 kilometer taper seemed like a reasonable option. You still have a good amplitude of the QBO with that one. So then we're left with this as perhaps our kind of optimum grid for the purposes of having a good QBO. And this would leave us with a 91 level model after boundary layer upgrades. And then these other ones are kind of still options. We reduce computational costs, but we'd likely be compromising on the representation of the QBO. So before making any final decisions, and this is where we were at the last meeting, we wanted to move to the spectral element dynamical core to test this out in another dynamical core. So the finite volume one, all of those tests have been done with finite volume, and that is not going to be the workhorse dicore for the next workhorse version of CESM. And one of the candidates is the spectral element dicore. So we wanted to try this out there and see if we came to similar conclusions. And so in SE, we can get a good QBO. We haven't done quite as much tuning of this as we did with the finite volume for the period. And so when we look at the amplitude here, I'd shown you the solid lines before, which are the FV ones. Now in spectral element, the amplitude is pretty similar between the 500 and the 700 meter case, but we have not really tuned in great detail the QBO. But one feature that I think Rolando considers to be very important, and if we have this, then we have promised that we can tune the QBO, and that's these composites of the descending westerly phase and the role for the resolved waves in driving that descent. And we see the same dependence on resolution. In this case, the 500 meter grid spacing has a role for the resolved waves in driving the descending westerly phase of the QBO, whereas the 700 meter one doesn't. So there's hope that we can tune the QBO to have a better amplitude in the 500 meter case. So then we went to configure a low top version, and we wanted to do this before messing with the boundary layer because we wanted to tune up the boundary layer one in this low top configuration. So we came up with this grid, which has the same 500 meter resolution in the troposphere, but when we taper it off more rapidly at about 10 kilometers, and then have a model lid that's about 40 kilometers, which is similar to our current CAM lid. And one thing we learned here, which Julio mentioned before, is that we do need to do different things with the gravity waves at the upper boundary for these two models. So here I'm showing the tendencies due to gravity waves in the 110 level WACCM. So this is what the gravity waves would do if they could propagate all the way up. And so you see that a lot of the momentum is being deposited at around 80 kilometers. And we found that in the 80 kilometer model, if we don't dump the gravity wave momentum at the model lid, the vortex becomes too strong, particularly in the southern hemisphere, and we have too much variability in the zonal winds near the model top. Conversely, if we dump the gravity wave in the 40 kilometer model and dump the momentum at the lid, it really messes with the structure of the stratospheric circulation. And that's because that lid is just too far from where the gravity wave drag momentum would be deposited naturally. So we do need to do different things with the gravity wave drag at the model lid, but I think there's justification for doing that. And so even though this low top configuration doesn't have a well-resolved stratosphere, it certainly doesn't have a QBO. It looks reasonable in terms of the basic features of the stratospheric circulation. Here I'm showing the wintertime polar vortices compared with the reanalysis, and it looks very much like our current low top CAM does. So the final thing we're doing now is to configure the new boundary layer. And so I'll just zoom in here. So this is the proposed grid that was configured by Brian Medeiros. And so the blue is our old boundary layer resolution, and the red is a new one. So the lowest model level has been lowered down to 17 meters, and there's 10 extra levels in the boundary layer. And so there were initially some issues with this crashing, and Julio can probably speak more to the details of this, but there were points that were partly over ocean that were very hot, and you were getting large humidity differences. And this was leading to instability in the Mononobikov calculation and leading the model to blow up. And this has been debugged and fixed thanks to the efforts of Julio, Cecile, and Bill, where they put a limiter on these constants, if that means anything to you. And this is found to not be climate changing with the original boundary layer resolution. And it allows this new boundary layer resolution to run. So these simulations are running and they don't look totally crazy. There's some shortwave cloud forcing biases. This is the difference between the old and the new grids. And these are currently being tuned by Cecile. So to conclude, for the next workhorse version of CESM, a 91 level configuration is being proposed, which has a top at 80 kilometers, a vertical grid spacing of 500 meters in the free troposphere and lower stratosphere, a lowest model level at 17 meters and 10 extra levels in the boundary layer. This will be accompanied by a low top configuration, which ultimately will have 58 levels. The primary feature that is impacted by the vertical grid spacing in the free troposphere is the QBO, and this configuration should have a QBO that is good, but we expect there'll be additional unforeseen benefits, both things that we haven't looked at yet, and then as we go to higher horizontal resolution as well. And so I think in discussions with the SSC, it was kind of decided that if we're going to take this step now to enhance the vertical resolution, we might as well go to this kind of one that we think is the best, and it will last for the next decade or so. And if we didn't take as large a step now, we'd likely need to adjust it sooner. So that's all I have. Happy to take any questions, or we can move to the discussion about this. Let me stop sharing so I can see the chat.
There's a question from Rolando.
Yep.
Yeah, hi, that was a very nice presentation. I just have a question regarding what you do with the vertical resolution in the stratosphere. I mean, clearly 500 meters in the upper troposphere, lower stratosphere, it's pretty much what's required to do properly the QBO. So that seems to be the case. I don't think at 700 you're going to get a very good QBO, or you may be getting something that looks good for the right reasons. The second question is, what do you do to taper off the resolution above the middle stratosphere? And I have said it before, I will say it again. Tapering to something like 6 kilometers renders the model useless as a stratospheric model. I mean, I think you need to keep it to about 3 kilometers maximum at the top. Otherwise, you're going to screw up the stratospheric dynamics, and that's going to have consequences for things other than the QBO, in particular the ability to model sudden warmings and the influence of the latter on the troposphere, which seems to be an important topic for people doing S2S forecasting. We are talking about maybe another 10 levels if you don't taper to 6 kilometers, but you taper to 3 kilometers instead. And that's going to be something of the order of 50 to 20% of the total number of levels. It seems to me that that's a false economy to taper to such a coarse vertical resolution above the middle stratosphere. And that's all I have to say.
Well, I think the thinking is that that's in the sponge layer anyway, so it's already kind of useless. But I don't think there's value in adding 10 more levels in the sponge layer. But there was the possibility of the grid where we stopped tapering and we maybe just need to add 1 or 2 more levels. And I feel like that is something that we should maybe talk about more before we make the final decision. But we are going to have to but there was an issue. Yeah, if we don't add those extra levels, there is an issue with lowering the model top and keeping the higher resolution. And that issue may depend on which die core we're using, depending on how the sponge layer is behaving.
I mean, my point is you are talking maybe 90 levels versus 100 levels. And what I am saying is that 15% extra levels, it really is piddling in the greater scheme of things. And if you want to have a model that is going to be good for the next 5 to 10 years, I really think you need to pay attention to these things.
Yeah, I mean, I guess we should probably discuss that more because I don't see the value in adding 10 layers in this sponge layer.
Well, I do, for the reasons I have already explained. I think a model with 6 kilometer vertical resolution in the stratosphere is useless, right? And it will create problems we want to build WACCM on top of this workhorse model. It will create problems for our building WACCM on it as well. Anyway, we can discuss offline. I think I've taken enough.
Well, maybe we can discuss in this half-hour discussion session.
Yes, we can do that as well. All right, thank you.
There are a couple of other questions in the chat, Isla. Do you want to look at them or?
Okay, is anyone looking at the SAO? I don't think anyone has, as far as I'm aware. So yeah, if anyone wants to, that would be good. Where does the sponge layer start? I don't know if Peter's here. Does he?
Yeah, if Peter Lauritsen's on the line, maybe he can field that one.
It depends on the die core, but the current configuration we're running, we're increasing the fourth order hyperviscosity about 10 levels down, but the serious damping with a Laplacian operator is the top 3 levels.
So do you think 2 grid points per scale height is a minimum for resolution in the boundary layer? I mean, in the sponge layer?
Yeah, that when with the old cam top at 40 kilometers, it was much easier to keep the model stable. But with the higher top, we kind of need to increase the sponge a little bit to keep the model stable. And we don't know yet how MPAS and FE3 will perform with this new vertical resolution.
So should I go back to showing to the resolution plot to see? I mean, how many levels would we need to add to accommodate this?
You want to do that? Go. I can quickly field a question from Tomas. The answer is that no, we didn't change the internal club time step with the increase in PBL resolution. It's still, I believe, 300 seconds.
Okay, so the idea is that we would need to have not go lower than 3 kilometers. Is that your argument, Rolando?
Yeah, yes, that's what I will propose. 3 or at the very most 3.5. 3.5 will be roughly half a scale height in the stratosphere. And
okay.
Yeah.
So we're talking about 40 kilometers divided by 3.5. So we're talking about 10 levels.
If I may interrupt here, the top 3 levels is where I would say solution is completely useless because we're damping out very large scales. The increased Del 4 damping, so hyperviscosity damping, is selectively damping gravity waves, and that's what is, the top 5, 10 levels. So that will go down to 50-ish kilometers.
So above 50 is where there are other things that would be making the simulation less useful, so we perhaps shouldn't be worried about it.
I'm just saying that it's the top 3 levels where we really can't look at anything. It's the top 5, 10 levels currently where we're damping divergent mode strongly, and we haven't played around with it much if we can get away with less layers, but this was a conservative approach to get us going.
And is it possible that the spacing itself is assisting the sponge layer to work properly?
I think it can. We haven't played around with it much, but I heard from the MPAS group, for example, when they're usually running with much higher vertical resolution. And they're able to get stable simulations without this Laplacian damping that we currently use in CAM.
Okay, so we should be thinking about maybe doing this taper and then keeping things constant up to, say, 60 kilometers and then tapering.
I think that seems reasonable, but I think obviously something we're going to need to look at.
Yeah. So just one last comment. It may be better to do this offline, but my feeling is that the grids that taper to about 3 kilometers at the top after having resolution of about 500 meters through the middle stratosphere are the most defensible ones in terms of stratospheric dynamics. And once again, the number of additional levels as a percentage of the total number of levels is small. We don't have any problem with adding 10 layers, 10 levels to the boundary layer. I understand that. So I just want another 10 layers in the stratosphere, that's all.
But we have gone from 30 to 90, and this would now be
right,
to 100.
If you're gonna do things, do them right. I mean, we have a new machine that is supposed to be 3.5 times the capacity of Cheyenne coming next year. So let's use it.
Okay. A question from Peter. The impact of different boundary layer spacing was striking. Do you know which parameterization is so sensitive? I don't know. Is it club?
I'll wild guess and say that it's probably Zhang-McFarlane, which currently has not been modified in any way other than, well, it's drawing its cloud-based properties from a layer that's now half as thick as it was. So we're in the process right now of, adding some options to Zhang-McFarlane that might average or do something for the cloud base. Yeah. So are there other, just general comments on this entire process? I'd be curious. I think we'd all be curious to just get input from, as much input from the community as we can. Last year we did send around questionnaires. Maybe later I'll show some results. So Joan asked a question to Isla.
The one about the time scale for finalizing the development work. Well, I think the hope is that this would be finished, the configuration of the vertical grid spacing would be finished in the next month or two, because then we need to start the process of the DICOR evaluations, and the plan is to do that with this new grid. So yeah, hopefully in the next month or two. And there's a group that, yeah, people here might not have heard about this, but that at Scripps that have a big computer, and they would like to run some simulations with this grid. So yeah, they're keen on getting it set up there.
Thank you.
More comments. Andrew is pointing out that this 80 kilometer with 90 vertical levels is probably close to what MPAS is using.
Yeah, I think when I got the MPAS grids for another talk to compare, and I think this is in terms of free tropospheric resolution is kind of in between where MPAS used to be and where it's going. So MPAS is going to a higher resolution than what we are having now, what we're going to, but we're getting towards what they had before. And then Rolando is saying one problem that must be solved is the dehydration of the upper troposphere, which Nick mentioned. And yeah, I think Rich is on that.
Yeah, we understand why the tape recorder gets drier, and it comes from the troposphere, and especially the wet phase, which is not controlled by cold point temperature in WACCM. So somehow that needs to be solved before this is a usable model. But you know, I am confident that you guys will be able to solve that.
And that's right. That's another modification to Zhang McFarlane, right? At least that's our feeling at the moment, that this has to do with how Zhang McFarlane is deciding not to convect deep.
Just a general comment that it seems to me the push to raise the lid normally to 80 kilometers was because a lot of the other climate models had their lid at 80 kilometers. But I'm a little concerned that here it's sort of 80 kilometers in name only, and that really a third of the model domain is sponge layer in altitude. And so, you know, I'm
pretty sure that
I'm curious what the vertical resolution in the other high top, quote unquote, high top 80 kilometer climate models is above 50 kilometers, and whether or not they see an advantage in terms of getting the right kind of trends and influence on the upper atmosphere down into the troposphere. If we need a 30 kilometer sponge layer, then that's fine. I mean, it just means that I think it bolsters the argument that WACCM is still needed for a lot of the stratospheric studies and the influence of the stratosphere on the troposphere.
But you're advocating for us to explore the sensitivity to the depth of the boundary layer as one way of kind of, I don't know, increasing the value of this model.
You know, I just feel like maybe are we really doing much different than we were before? Here you've tripled the resolution, but really only raised the effective lid 10, 15 kilometers. So I'm just wondering, is that?
Well, yeah, we did have I mean, this came up before, and there was the idea that maybe we should not have as coarse resolution and just have a model top that's lower. And we tried that, and it totally messed with the QBO. So I think 80 kilometers is kind of the lowest we could have the lid. I guess the question is, do we want to have more layers and make it more expensive? And I guess comments have been coming in the chat that, yeah, other people who don't have access to the same amount of computing time will be wanting to run the model. And so,
yeah, and also that it's you're always trading ensemble members for vertical resolution and horizontal resolution and complexity in club and all the other things. So, you know, it's the total cost of the model we have to consider here. Right. And the more we make even the workhorse model expensive, the less there is opportunity for us to actually improve things like aerosols and chemistry in the model.
Yeah.
Yeah, I think Isla, you've done a fantastic job in leading this effort with a lot of people's work to really document this. But we, as Dan is suggesting, we may need to step back, and that there are a lot of compromises in trying to go to one model, and it's trying to expand certain things into the primary configuration, but that or the workhorse configuration, but that may be too costly for people. And so at some point, the working groups probably, and maybe this is the time now that we need to, we have a series of proposed configurations now. They're sort of the 40 kilometer, 80 kilometer, and the WACCM version, and maybe even something lower. And we need to understand what are the trade-offs in changing those configurations and increasing the vertical resolutions versus the cost, and what specific science you get out of certain things. I mean, there has been a lot of discussion from Rolando, Dan, and others about what the science value is in each of these different configurations, but there are compromises that may be problematic. It's likely we still need something like WACCM, that we can't run one model for everything, because as Dan was saying, if you want to have chemistry and stuff, then even maybe 60 levels is too expensive, because we'd rather have more chemical constituents. So I think we need some way of capturing the community's, this groups plural, needs and prioritizing that can then go as a proposal to the SSC about multiple vertical resolutions and what science we expect to be done with what model.
Yeah. I totally agree.
Yeah. Okay.
Sorry, carry on.
I just was going to share the some of the results from our questionnaires last year. I don't know if that it's tremendously useful, but can everybody see? I mean, we just to summarize, I think, the enthusiasm for increasing the cost of the model to get, better stratospheric dynamics, it was, in the AMWG questionnaire, it was about 50-50, which I think is a fairly high level of interest. But what really struck me is that what the community seemed to want was more capability to do, to do configurations on their own. And I think that's kind of where to me, that's the discussion that I think we need to have. And that is, at NCAR, we cannot, it's not realistic for us to maintain, both a cutting edge model as well as, a suite of more economical models that are basically they're still fully coupled, et cetera. So I guess a question that I would have to the community is, what is a reasonable, balance between asking people in the community to develop and tune versions of the model given good tools versus, taking fully vetted configurations from NCAR. And I'll stop sharing at this point.
So maybe, I see Gokhan raised his hand right before I started talking. So,
well, I just wanted to mention that, I mean, this is not a new effort. We asked about these things to the community, and it almost started 2 years ago. And some of the questions that are being raised here, they have been already raised multiple times. And I think there were quite a few discussions. And as Julio indicated, CESM itself cannot support everything. I know that there are multiple sort of competing interests from the community with many dynamical cores, many configurations, but we cannot really address all of those at the same time. And perhaps, I mean, providing the tools for the community to do these things would be, I mean, is the approach that we can take. But, and we cannot really spend another 2 years trying to get what dynamic or not dynamic core vertical grid that we'll need and what high top or low top that we'll need, because we have to consider other things such as dynamical cores and many other things are looking at how we are going to proceed with this. So I just wanted to remind people that these are not new issues. And it has been on the, whatever the discussion items for the SSC for the last 2 years almost. And anyway, I'll just stop there.
So why don't you go ahead, Kevin?
Yeah, so I mean, and just it's related to kind of, I think, what Gökhan mentioned, but also, I know that part of our discussion we had last year was, I advocated pretty hard for a survey, kind of like the one that was put out. And I think what might be beneficial without doing what I think Gökhan is suggesting might happen is if we just keep having this discussion, we'll never get to whatever our workhorse model is. I mean, we'll get there eventually, but maybe we're just kind of, just going in the same cycle, where it would be to have some type of follow-up survey to last springs that is a little bit more specific, right? Because when you have open-ended questions, you get feedback, but the feedback might be different when you say, would you like a version with this amount of vertical levels or this amount of vertical levels? Here's the pros and cons of each. Which one is your preferred kind of workhorse, or which one would you use most in your science? And that's a little bit different than I think the last survey. And so maybe it would actually help kind of take some of the outcomes of the task force or task teams and kind of actually just get the temperature of the community within a, one or two or two or three configurations, I suspect. That could be useful, but I want to follow up. But the other thing is, I as somebody who's constantly, using the model and changing resolution, doing different things, I do think that if there was a little bit more, if one of the things, and this is beyond just the AMWG and these working groups here, but if there was almost like a recipe for, if I want to download the model and let's say I want to change the vertical resolution or I want to change the horizontal resolution, is there I know we have the benchmarking and the metrics that are used to assess kind of whether a model is validated over a certain time period, but making those almost a little bit more user-friendly to somebody who's just running the model, has the default output and wants to see, how does it stack up compared to the official workhorse version in terms of, error and the, and top of the atmosphere energy balance and these type of main metrics that are used. If it was kind of almost easier to kind of see directly where it was. And I know that it's possible to do that. I think that it's just maybe we need more, I guess, documentation of how a university user could do that on their own.
That's great.
Yeah, I think we can. I feel like one of the things we learned with all of this vertical resolution investigation is that we can change without messing with the boundary layer. We can change it between 500 and 1,000 meters, and not a lot changes except for the QBO. And so if we can document that, and then people could be flexible to choose their own vertical resolution, knowing that it's not totally supported, then maybe that would be okay.
Yeah.
And the other issue, Isla, is the vertical top and where you place it. And if you start placing it low, you have to change the gravity waves.
Yeah.
Just the way they propagate, at the top in the sponge layer, so that you actually don't mess things up. So, I mean, that could be added to a, lessons learned document that would make it easier to, degrade or increase the resolution for your particular problem, but keep it benchmarked against things we've already done.
Yeah.
So Thomas has been waiting to make a comment. He has his hand raised. Do you want to go ahead, Thomas?
And thank you, Isla, for a very nice talk. I second what Kevin has been saying, but also perhaps you mentioned that you want to do an impact assessment of this increase in model levels, and it would be really good to do that, I think. Because we all know that currently the lead of CAM is too low. We also know that the resolution, particularly in boundary layer, is really bad. And we know that the resolution in the mid-troposphere is not great either. So I think everyone is aware of these limitations of CAM, and there is no questions that the number of levels need to be increased by a substantial amount. So a factor of 2 is something that we expect. And that's fine. But it would be great to see actually a good evaluation of this. So I just mentioned the fact that we are experimenting here with PBL layers only without changing the rest, just to see what the impact is there. And we have been discussing this a lot, yes, in the past about vertical levels, but yet I still see in the presentation of Ayla, which I think is very good and very interesting, and I find it really scientifically exciting. Nevertheless, the entire discussion is verting around the QBO. The QBO is not the only phenomenon in the atmosphere. You have a skewed evaluation there of these increasing vertical levels at the moment. So well, I think, we can improve on that, and we can maybe collaborate by looking at different impacts of refining in one place rather than in another, perhaps.
I did say at the beginning that we looked at many other things, and I didn't talk about it because there was really no difference. And so that's really the reason for the focus on the QBO, is because it's the one thing that primarily seems to be sensitive. At least, well, once we go to the boundary layer changes, I think other things maybe become sensitive. But
exactly. So this is, I suppose, the point I'm trying to make. For instance, I had to change the club time step because otherwise the model would crash. I did not have to do anything in the RC flux computation because I'm using the core scheme, which is not sensitive to those minimum conditions that the large scheme is using. So I encounter a different set of issues by doing the same exercise that you are doing, but basically changing my choice of boundary layer representation and vertical level distribution. So maybe there is scope for finding out a little bit more.
I'll just mention maybe that Xiaohong had also talked about the impact on clouds, which I think is something we haven't been looking at a lot. Dan Marsh has his hand up.
Yeah, just one comment that I think perhaps there's a little too much baggage associated with the term workhorse, and that, we should be thinking about being able to have people use this as a flexible model now. And maybe we spin off or just have a small group focusing on what is to be used for the next CMIP, because that occupied our old computer for a year and a half, 24/7 on how many thousands of CPUs. And that, yes, that there should be some focus on that, but I don't necessarily, it means, I like this idea about giving the tools to allow people to use the model in flexible configurations as almost an equal effort here, and we're not going to say this is the model for everything, but give people more flexibility to have scientific trust in a configuration they have with the model.
Right. Yeah, no, I think that's a great. I like these comments, and I think that it's really addressing what I think is a kind of an insoluble pull in two different directions that our group has. We want to have a cutting edge climate model, and we also want to support the community using a model that is, runnable on by people with varied resources.
Julio, I just wanted to.
Could I make a comment on that? Sorry.
I can't hear I don't know who's talking.
This is Rolando, but I have lost my ability to raise my hand, so I had to interrupt. I have a comment on cheaper models. We do have a 2-degree version.
That's right.
Of these models. I mean, if you want to go cheaper without, essentially rendering the atmosphere above 100 hectopascals unusual, you may want to consider dropping down to 2 degrees from 1 degree. That's another possibility, and that can be built immediately. There's really nothing much that needs to be done there.
Good point.
Julio, yeah, it was me actually, Gökhan. I just want to mention that this essentially push and pull or whatever, we are seeing it in all the working groups. It's the ocean model in the same boat as well, and others. Everybody wants sort of maybe it's a loaded term, sort of a standard version of the model they want a high resolution version of the model. There's also desire for ultra high resolution version of the model, as well as simple models. So we are being requested, and this is going to be reflected in the CESM strategic plan in a hopefully balanced way. And this is coming from, I mean, many groups. And this, I mean, because CESM is community, it's not surprising that we are getting these requests. But I also want to remind you that it is not just necessarily providing a single version of, or whatever is particular configuration or resolution version of the atmospheric model. It's a coupled system. It is unclear how a particular resolution version of component A will interact with another particular resolution version of component B and C for that matter. So that's where the sort of the resources needed and all that stuff. So it's not an easy task. It's easy to say we need 2-degree version is running. Yeah, but we don't know how it's interacting with other components essentially. So those are resource intensive exercises. But I mean, it's not surprising that we are getting these requests. So,
I mean, I think the 2-degree might be a little more. I mean, that has been vetted in
vetted more, right?
Way. But you're right. I mean, providing tools for people to tune the atmosphere does not address the impacts this might have on the ocean, the land, et cetera. So I don't know if Dan, do you have another comment, or I know Adam also has his hand up.
I don't know how to lower my hand. Sorry.
Oh. All right.
Yeah.
You want to go ahead, Adam?
Well, yeah. I mean,
oh, there we go.
It's funny, Gökhan and Julio, you both just sort of expressed what I was thinking. Is that, you know, providing the user with directions to configure grids various ways, it works really well for atmosphere-only simulations. But as soon as you start coupling with the ocean, you basically need to know how to tune the model. And I'm not sure that that's something that we want to unload onto the users.
Yeah, I mean, that is a big task. That's what I was alluding to essentially. And that's why we need to be a little bit sort of limited, maybe careful or judicious in our choices of coupled supported systems. And so that we can essentially check the TOAs and all that stuff.
Yeah, I mean, I agree. It's not a trivial exercise to develop a coupled model, but yeah, I think we do need to, you know, our resources at NCAR are limited, and you know, we do have to. I think this is an important thing for us to kind of grapple with. I do think we might want to have more faith in what the community can do with you know, with maybe some guidance from NCAR, but not relying on the CSM groups to provide every version that's available for use. So Isla had to leave. Are there more comments? Okay. Well, I think one thing that I know we might do is to impose on all of you for with another questionnaire more along the lines of what Kevin suggested, more specific, maybe addressing some of the questions about, you know, providing tools versus fully vetted models, et cetera. If nobody has anything they want to raise right now, I think we can go ahead and close the session for this morning. I don't remember when we start up again. I think it's
1 p.m. Mountain Time.
1 p.m. Okay, so in
less than an hour.
Okay. All right. So then why don't we close up for the morning and come back in about 50 minutes. Thanks, everyone.
Hi, Julio.
Hi.
If you are going to step away, can you share your screen with the agenda?
Oh, sure.
So the meeting stays open and the YouTube stream still runs,
Okay.
just so it stays as one continuous meeting. So that way, if people click on to the YouTube, they see the agenda, then they know what time it will start back up again.
Okay. Do you see it?
I do. I see your sidebar as well. You can close the sidebar.
Yeah, that's you're asking a lot.
Yeah, Chrome just changed, so it's. I think if you mouse over the thing, the right-hand side, you can at least find a plus sign to make it bigger. Oh,
There.
very good.
Hit the vertical bars there, and everything closed. So
That's perfect.
great. Okay. So yeah, I'm going to step away for a few minutes, and then I guess we'll be back at 1.
That sounds good. Thank you.
Yeah. Thanks. Thanks, Elizabeth.
Sure.
So Julio, did you want me to
Do you want to
share this session?
Sure. If that's okay, that'd be great.
Sure. And it's exactly 1 now, so maybe we should get started. So let's see. So first, this is the clouds and physics section, and Joao is going to be our first speaker, telling us about EDMF. So Joao, do you want to take it away?
Can you hear me?
Oh,
yep, we can hear you.
And I'm trying to share my PDF. Can you see it?
We can.
Is it on, which mode is it? Is it on the display mode or full screen or not? It's not, right?
Certainly not on display mode.
yeah, there's a share icon. I'm not sure what we're, are we looking?
Is this better?
Now it all looks black to me. I can see the top panel, but other than that, it looks all black. Maybe are you sharing the
just sharing. Oh, now.
Yeah,
so, yeah, we can see the whole thing.
Let me make it big.
You know, I think you just have to go into your
is that
viewer
good?
and turn off viewing the bars, the sidebars. At least that will help.
Yeah. Yeah. So maybe if you hit the green plus, I don't know if that'll make it bigger. It's certainly we can see like the tops and the sides of the options.
Is that better? Should we go ahead with that? I just don't know what you're seeing, but just tell me if this is visible. Is this visible?
It's visible, yeah. I think it's probably good enough.
Yeah.
Okay. Thank you for your understanding. Thank you for the opportunity again. It's a great pleasure to be able to say a few words about our most recent project. So I will try to be very brief. We have a new eddy diffusivity mass flux CPT project. Started about a bit more than a year ago. This is the list of the key participants. I'm going to the next page. Oh, okay. So I guess I have to do something like this. It's ugly. Okay, so I hope you're seeing the second page. I won't dwell on this. The goal is, of course, to reduce key biases related to the physics of the PBL, clouds, and deep convection, both the NCAR and the GFDL model. We are focusing on the PBL, but also the PBL in the context of transition to deep convection to show how, how feasible it is to develop methods that are fully unified in terms of unifying PBL, shallow and deep convection. I'm the lead PI. Julio Bachmeister, Leo Donner, Rong Fu, George Matteo, and Michael Weedy are the PIs. And as you saw before, there's a longer list of key participants. So I'll go to the next slide. Again, I won't spend too much time on a lot of the details of EDMF. Essentially, EDMF is an attempt to sort of integrate different parameterizations of mixing using eddy diffusivity to do the small scale mixing, and plumes that do the sort of the PBL convection scale mixing. And the idea here is that you do it from the beginning. So in the sense that from the equations themselves, the algorithms, the code, they sort of integrate at birth in a way, and not just different modules put together in sort of an artificial way. So the method that we've used most recently, and that the one in which we sort of will take some of these aspects into NCAR and GFDL, is one that is based on the idea of the plumes themselves being multiple plumes or multiple thermals in the same grid box. You draw from your sort of surface layer PDF of thermodynamic properties. In addition to that, you have a stochastic lateral entrainment, and basically the initial properties of the plumes close to the surface and the stochastic lateral entrainment would sort of decide the fate of each one of these plumes, right? So if a plume entrains too much, then that plume will not likely go very far. The key aspect of the entire story, I think, And one of the reasons why we went for multiple plumes or thermals is the idea that in the same grid box, you can have coexisting different types of convection, right? So you don't have to change from one regime to the other or blend them together in some sort of odd way. You do have multiple plumes, and as such, you can have plumes that only go up to the subcloud layer. Others become moist shallow convection, and even others could become deep convection. So I won't show too many of the results. I mean, the references are there. You can look at them. I'll show you just one result in the context of the fact that what we're trying to do is really to bring some sort of integration or unification of mixing from, let's say, the stable boundary layer, dry convection, shallow convection, and moist convection. And the result I'm showing you here is one of these latest papers that I have described in the previous slide. And here what we're doing is simulating the LBA case, is a transition to deep convection case. You can see the left plot is height versus time, and in there you have the cloud base and cloud top from both an LES experiment and an ensemble of EDMF realizations based on the approach I just described in the previous slide. And then on the right, you have the cumulative surface precipitation for the same models. And what you can see is that, and you can look into the paper for more details, you can see that as long as the plumes have some sort of adequate, and by no means we think we found the final solution for plume microphysics or downdrafts or gold pools, but if you have some sort of adequate parameterization of those effects, then you can indeed have a sort of smooth transition from stable boundary layer to dry convection to shallow convection, and finally to deep convection, all within the same parameterization, all within the same scheme, without having to jump from one particular parameterization to another one. But in any case, let me move into the CPT. So first, I would like to highlight the fact that large eddy simulation has been and will continue to be a fundamental tool in everything we do. George Mateo, who's one of the co-PIs, has developed an LES model that is quite realistic and very faithful to the observations that he has used to sort of evaluate the model. These are just some images from a particular experiment, from a very large domain RICO experiment. One of the aspects of the CPT that we are focusing on is to develop more and more complex LES sort of frameworks, and George and his team are working hard on this, and hopefully soon he and his team and us in general would present some of the results.
Did everybody lose Joao?
I think so.
Oh,
No audio here.
Well, this is an awkward situation.
because can he hear us? He should be able to hear us.
Sometimes he's got a pretty weak internet connection. We do have his slides. We can give it 30 seconds, wait for him to come in, and if not, maybe Julio or I could.
That sounds like a good plan. Do you think, Adam, do you think that you could actually give his presentation, or are you saying that just you could change the slides for him?
Well, on further thought, maybe I should just give my presentation and give him time to finish his after mine.
Yeah, I think at this point he's been gone for a while, so let's do that. Thanks,
Yeah.
Adam.
So I'm going to share my screen.
I'll email him in the meantime.
Sounds great. Thanks, Julio.
Okie dokie. So it's 1:08 right now, so I'm going to try to keep it under 15 minutes. So yeah, I'm going to give a detailed description of the NCAR implementation of the EDMF CPT that Joao is describing. And so I'm going to give a very technical talk about some of the design decisions that we have to make when we're implementing in the mass fluxes in a club. And I want to do that to just sort of be very transparent, because I'm really striving for longevity in this project. You know, this framework has the potential to replace the Zhang-McFarland deep convection scheme in a unified way, which is what we're hoping for. So first I'll start with just a quick overview of moist convection in CAM-6 proper. This is sort of the workflow of the moist convective processes in the physics package. And so the Zhang-McFarland scheme is called first, and you take the heating and moistening and apply that to the state. You end up saving off the liquid detrainment to be handled later in the macrophysics routine. Then you sort of enter these big macrophysics, microphysics loops. And so club will advance its turbulence and then do a saturation adjustment acting as a macrophysics routine. And then the ZM detrainment will get applied. And then we go into the microphysics, and because club does not deal with phase changes of ice, microphysics, the MD2 will sort of retroactively take club's cloud liquid and partition it between liquid and ice, advance the microphysics, and then loop through this some number of times. And so the idea is to bring in the mass flux into the club oval here. And so I'm going to blow up sort of the workflow of this interface that we're working with. And one of the main challenges in really just coupling CAM to club is that club works in these moist conserved thermodynamic variables, liquid water potential temperature, and total water species. And so these are their prognostic variables, whereas CAM just works in these regular non-conserved variables, temperature, vapor, and liquid. And so the first step is obviously you have to convert CAM variables to club's variables. Then you can go into the big club computational loop. And so we decided at the top of the loop, we're going to compute this ensemble of mass flux plumes, which could give us a cloud fraction that we could feed to radiation. And then we pass the divergence of the fluxes of QT and theta L. We kind of fork it right into the guts of club, into its mean equation solver here, which I'll go into more detail about this later. Then club kind of goes through and prognoses its other higher order prognostic moments. And then it uses those to compute a new double Gaussian PDF, and it does a saturation adjustment. Now, so this is the cloud liquid at the new time step is extremely relevant because it is the only thing that we have to convert from theta L at the new time step back to CAM's temperature variable. And what I want to highlight here is there's an assumption that we're bringing in with these mass fluxes, and that we're actually providing a source of cloud liquid to the club environment with these divergence terms. And we're sort of assuming that the cloud liquid from the saturation adjustment at the end of the club call faithfully sort of represents that detrained cloud liquid that's coming from the mass fluxes. And so that's an assumption that we just need to keep in mind, because with theta L, when you evaporate cloud or you condense vapor to cloud, theta L does not change. And the only way you realize that heating due to cloud formation is in this conversion back from theta L to temperature. So now I'm just going to talk about sort of the mass flux model that we're using, which I think it's called, I call it surface-driven convection. And the point here is it's a very different animal than sort of the convective quasi-equilibrium schemes that I'm used to working with, like the Zhang-McFarland scheme. And the idea is that, and Drow mentioned this a little bit, you have like a convective velocity scale that is effectively representing the surface buoyancy fluxes from the host model. So it's a very local convective velocity scale to what's happening at the surface, and then has some memory in terms of it's multiplied by the PBL height. And so this velocity scale you can use to sort of back out a theta V scale and a QT scale from their relevant host model surface fluxes. And from there, we sort of back out the subgrid variance of W, QT, and theta V via relations between these scale parameters and their variances, which are set to some constants that we derive from LES. And then we can initialize the plume ensemble beginning at the surface. And what we do is we basically take the vertical velocities and we sample them between this portion of the PDF, 1.5 sigma to 3 sigma. And then from there, we can back out the surface values to initialize the plumes for QV and QT using some assumed covariance with W that, again, are constants from LES. And so the reason I'm going through this is there's a lot of free parameters so far already, which I think is important to explore in the future. So then you can sort of integrate your plume profiles vertically. We use a stochastic lateral entrainment rate. And then we can compute a buoyancy profile and integrate this steady state plume equation. And so just to give you a flavor of what this type of surface-driven convection looks like, you basically, this is the gate case, and this is just the divergence of the theta L fluxes. And what you can see is you really do, as Drow was just mentioning, you can do sort of nice transitions between sort of convective boundary layer to shallow convection all the way up to deep convection in sort of a realistic way. If you compare a similar plot for how sort of the ZM scheme would interact in this same case, you can see that it kind of has sort of a binary approach where it's either sort of not very active or extremely deep and active. And, you know, one thing to keep in mind when comparing these two schemes, so two things. First of all, the theta L forcing tends to be the opposite of the equivalent of the temperature forcing. And so that really highlights the importance of making sure we are converting our theta L back to temperature correctly. And then the second thing is that, you know, the ZM convective quasi-equilibrium is really constrained by the large scale destabilization of the state. And so it's designed to remove instability in a GCM, where the surface driven convection should remove instability, but it's not constrained in a similar way to remove instability. And so I think that highlights the importance of all these free parameters that we have here that we might need to explore in order to make sure that this surface driven convection scheme is acting sufficient in a full GCM to actually remove instability. So those are the kind of the trade-offs of the two different types of convection. Okay, so how do we integrate these MFs into club? So this is the mean equation that's advanced by club here for total water. The mean advection is handled by the dicor, and then the club turbulence is handled as its own term. And then there's an optional forcing term that club provides us the option of providing to it. And that's where we decide to dump our MF plume ensemble. And so here's where we're sort of diverting from sort of more traditional EDMF approaches. I mean, first of all, the edit diffusivity is a high order prognostic model, i.e. club, so that's very different. But the ED and the MF fluxes are not summed together prior to taking their convergence. They're divergence operators. They're instead the divergence of the fluxes are taken separately and then summed. And so that means they may or may not have requirements for different boundary conditions depending on how we implement these. And so for the current implementation, here's sort of a schematic of a grid cell with the orange lines are the host model surface fluxes, and then the turquoise recycle arrows are club turbulence. And sort of like the view from 30,000 feet is that we want to conserve energy over a club time step. And so we compute a vertically integrated energy from the grid mean quantities before we call club, plus we'll add in the surface fluxes component to the bottom boundary that is actually applied during club. And then that has to equal the energy afterwards. And so to sort of satisfy this energy conservation, you know, the club state takes up the entire grid cell, and the club surface boundary conditions for its fluxes need to be equal to the host model surface fluxes. And the MF plumes sort of sit out here in sort of a virtual volume that doesn't really exist, doesn't really contribute to the grid mean state, other than providing these forcing terms to the environment. And so this also requires that the surface fluxes, the boundary conditions are 0 when we're doing the divergence operator. So alternatively, we could do something a little more general and turn it into a 2-volume problem, in which case your state after the call will be the area fraction times the MF plume state. So these are the plume profile, so the ensemble plume profiles are contributing to the grid mean, plus the area fraction of club times the club state. And in this situation, then we need to make sure our boundary conditions for both club and these MF plumes are equal to the host model surface fluxes to conserve energy. And you may recall that we have we kind of determine the surface fluxes in the MF plume from that prior slide. We determine it from all those assumed PDF, LES determined coefficients or whatever. And so, you know, in the actual divergence operator, we'd have to scale those to satisfy this constraint. This sort of provides us with some flexibility in terms of, you know, if the plume ensemble area starts to approach the environmental club turbulence area, you know, then that is reflected in the grid mean state. And so that has the possibility of being a more scale aware parameterization. And the way that we do actually compute the areas in the MF plume ensemble, so we have that number. So the only issue I think with this is it might not be consistent with the CLASP framework, which really wants to pass the surface heterogeneity to club's variant solvers and utilize it. And we don't have that capability in the MF plumes. And so I'm not sure this is consistent with the CLASP vision, but it is a choice. So let's see, 18, I'm at 13 minutes, so I'm gonna skip over. Okay, I'm gonna show this last slide that just shows you how nice it is that we're using the same solver to solve for MFs and club at the same time. This is the club grid. It's staggered in that your midpoint levels have your mean quantities and your fluxes are at the interfaces. And they use a 5-diagonal matrix in order to actually solve for the related pairs of mean and fluxes simultaneously. So that is theta L bar and W prime theta L prime bar at the same time. And so the state vector is sort of staggered. This lines up with the vertical grid where you have fluxes, means, fluxes, means, fluxes, mean up and all the way down the grid. And so that's what we're solving for. And we do it by throwing in the coefficients for the fluxes and the mean equations. You know, I guess I shouldn't get too much into the linear algebra here. And then the point is that we're plugging our MF forcing terms into this right-hand side term, which is actually just explicitly integrated forward in time. So I'll stop there. Save for 10 seconds. I just want to say we have a version that's actually on the CAM development branch. It doesn't work well for 32 levels because we had to switch to an upwind flux scheme to do that. And that's not currently on the branch. And so some other things we have to fix is an energy conservation fix I have in there. Some more microphysical processes, downdrafts, cold-cool parameters. You know, revisiting how we sample the surface WPDF, which maybe utilize the club PDF in some way as well, and then potentially experiment with this 2-volume framework. So that's all I got. All right. So I will take any questions.
And I think actually sorry, echo. So the talks are supposed to be 12 minutes and you went about 15. So I think we probably need to move on. And in order to not get too far out of schedule, I think Joao, are you back? Could you give the rest of your talk?
Yeah, I'm back. Can you hear me?
Yep.
Sorry about so let me now try to do this with PowerPoint. That's probably better. So I'll just share the, let me see. Can you see it? Let me know.
Yes. Yes, we can.
Yeah. Yes, we can. All right. Perfect. So I'll be very brief. So I was here on the LES. It's very important, but let's that's when Julio said, I think we lost you. Let me just go and show some results. So 2 results from GFDL, 2 from NCAR. So we have a bit of a different strategy regarding the way we're implementing the mass flux into both the GFDL and the NCAR model. Adam already gave this wonderfully detailed presentation on all the issues that we have with trying to combine a higher order closure like club with MF. It's a really tough problem, but it's an exciting one. So with GFDL, we've done a couple of things. So one of the results that I think is most interesting is the fact that when we implement a dry mass flux, so dry plumes into the eddy diffusivity component of GFDL, so we basically solve them together, but we don't allow the plumes to condense. And this, the reason we do this is because not only it's kind of an interesting scientific question of how much do we eddy diffusivity models miss the dry convection part that is underneath the cloud or underneath the PBL top if you don't have clouds, and how important that mixing is from a climate perspective. But also we know that from previous model implementations that actually that in itself alone has an interesting impact. So this is work that Ishwan did and the team at GFDL. This is a 25-year AMIP run, and what he realizes is that the results from adding the dry mass flux, so just plumes that do not condense, is enough. So the impact is enough to actually be seen in properties like low cloud amount. So the top image is the low cloud amount from a control run, AM4, and the bottom one is the difference between the new EDMF with just dry MF plumes and control. And you can see that in the stratocumulus regions and in transition to cumulus regions, the low cloud amount increases by between 5 to 10%, which is actually quite a large number given the fact that there is already quite a lot of cloud there, although not enough. So that's one result, and this is being explored and tuned and try to understand better what the impact is on the overall climate. The second component, and the GFDL team has been working very hard. I move to the next slide. I hope you see that. It's entitled Implementation of Moist TKE and GFDL. So each one and others have done a lot of great work in implementing a moist prognostic turbulent kinetic energy closure in the GFDL model. To be precise, it's the MYNN version that is in the WRF code. And this is a lot of work, again, every time, and the experience with club that I know people at NCAR have, although club is even more complex, but just bringing a prognostic moist turbulent kinetic energy equation into the code in a climate model is a major challenge, although of course pretty exciting for someone that comes from the PBL turbulence world like I do. What you can see here, and the overall conclusion is that even in spite of doing absolutely no tuning whatsoever, the current version, and Ishwan and others have been working on this for the last few weeks, the current version of the GFDL TKE, moist TKE implementation is very comparable in AMIP runs to the control version, which is actually great news. This one is actually better. I picked a field, the liquid water path, which is a tricky one. At the top, you see both on the left, the GFDL control and the GFDL TKE, the new TKE on the right. And at the bottom is the same figure, it's MODIS. And you can see that if something, the GFDL TKE model is actually closer to the observations. Now, liquid water path observations are tricky, and the way you define them in observations in the model is also, it's not a simple field to analyze one-to-one sort of thing. But the encouraging result is that after a few weeks of work, the GFDL team is actually able to run the GFDL model with moist TKE in a comparable type of climate quality as the control version. So there's a lot of work here ahead of us in bringing the mass flux plumes into that. So news would come later, and hopefully successful news. Regarding the NCAR model, and I'll be very brief because Adam already talked about a lot of the details, but essentially from a 50,000 feet perspective, the idea is that club represents the double Gaussian mixing, while the plumes add some additional discrete skewness to the subgrid PDF that may not be present and may be necessary, and that's what we're trying to show. And that we solve the plumes and club, they are solved together, so the plumes are coupled to the 5-diagonal solver that club has at its core. So in a sense, they're integrated at the beginning as well. I'll show just 2 results. I think I missed Adam's first slide, so I don't know if he showed results, but if he did, and I'm just repeating what Adam said, I apologize, but you have the opportunity to look at the images again. So this is the BOMAX case, and I wanted to highlight very quickly 2 things. At the top, you have the cloud and cloud fraction and cloud liquid water. Black is LES. This is a steady state shallow convection case. Blue is club, and red is club MF. If something club MF is a little bit better, it extends, has sort of more efficient mixing. It extends a little bit higher than club itself. At the bottom, you have the fluxes of the moist conserved variables, both the theta L flux, liquid water potential temperature, and total water on the right. For those, we also decompose the club MF into the club tendency component and the mass flux component. And if you look, for example, at the theta L flux, you can see that club already matched the LES results quite well. In a certain sense, the club plus MF makes the flux a little bit stronger, which when comparing to the LES in this sort of second moment field, it seems to be a little bit too much. But if you actually look at the mean variables, it seems to affect it in a positive way. So maybe there is a balance there that the model needs a little bit too much flux to actually go deep enough. And you can also see what you would expect, that the MF component of club MF is essentially acting in the cloud layer, where you have this sort of additional discrete skewness from the plumes that is brought in on top of the double Gaussian. The last slide is just a relatively similar case, a bit more complex. It's the diurnal evolution of shallow convection, starting from a dry boundary layer over the arm side. You have 3 images. I hope you can see them. The top one is that temporal evolution of the temperature tendency from club alone. The next one is the temperature tendency evolution from club plus MF, and the bottom one is the LES results. And what you can see is, again, that there is more effective or efficient mixing when you add the mass flux plumes, and that in this case, this was probably necessary in the sense that club plus MF does seem to provide a growth of the boundary layer and shallow convection that is more akin to what the LES shows, and with the values of the temperature tendency, the cooling that is brought in by the plumes, quite similar to the LES and higher than what club alone seems to provide. So that were the main results. There's a summary slide that I can leave there if there's any questions. I probably went over my time, particularly by having that interruption. So but any questions that you may have on the chat, or can send my email, or I'm around, so I'll stay for the conversation at the end. So maybe that's best to talk then. So anyway, thanks, Peter. Thanks, Julio.
Okay. Thanks. Yeah, so we are about 3 minutes behind now, so let's keep moving, but do feel free to ask questions in the chat. So Chris Cruz, I think you're up next.
Okay. Okay. Can you see my slides?
Looks great.
Okay, first try. So I'm Chris Cruzy. I guess I'm working on this Momentum CPT led by Colin and Vince and Julio, and there's many other people involved. I'm roughly calling this talk CAM6 Errors, Attribution, and Some Paths Forward. I guess the objectives of the project, at least what I've been kind of thinking about and wanting to do, I guess, ultimately we want to improve club, and I'm really curious about this more complete momentum flux budget that Vince has worked into some of his versions of club. And I'm curious to see how that, that more physically complete momentum budget, if that improves CAM, or at least the tunability. But before we get to that, I guess what I've been working on is trying to evaluate CAM by identifying errors and attributing them to particular processes. And I'll talk a bit about some of the things that I've been doing in order to kind of do that. And then, ideally with identified errors and an idea of where they might be coming from, it's not necessarily club, but we want to, let's say it is, then we can, focus on club or another process like gravity waves or whatever, or deep convection, and then try and reduce them. So overall, again, I'm focusing on processes that influence momentum and club in particular. So, how do you evaluate CAM? There's a number of ways. All I'm going to talk about here is that I'm just trying to evaluate CAM in the context of runs that are nudged to reanalyses. So I'm looking at two different configurations of CAM. There's default CAM6, which is using club. And then out of curiosity, we're also looking at CAM6, but with club turned off and the older UW schemes turned on. Everything else essentially the same. In terms of reanalyses that I'm looking at, there's a 6-hourly error interim, 3-hourly merit 2, and I'll show some results where CAM is nudged to both of those. And I won't talk about it, but ultimately we're going to go to error 5 because it's hourly, and when you're nudging to a linearly interpolated state, you don't want only four states per day. Okay, so we've got these nudging tendencies in these nudged simulations, and so if we were to assume that because things are nudged, your time tendency of say U is correct. And if the state is more or less correct, the dicor tendencies that the dicor produce should be more or less correct. Well, then if you have nudging tendencies, then you can interpret those nudging tendencies as just a total physics error. And I guess that's an assumption that we started with, and I'll kind of come back to that. Just a quick side note, something that I've been working on is I've added a feature in CAM, which is working its way into, I think, the development branch. If you set history budget equal to true, or if you just specify these various variables in your Finkel, we now output a complete closed horizontal momentum budgets. And so all of these different variable U10 variables, there's also the V10 variables, can be output. And nice thing is like U10 tote is equal to U10 core plus U10 phys tote, and that does close to machine precision. And then your physics tendencies, that this particular variable is made up of all of these. It's every single parameterization routine that can influence the horizontal momentum. And there's some of these variables which are kind of legacy snippets of code, but I've included all of this so that as long as you sum up everything on the right-hand side, you will get your U10 phys tote and your budgets will close. And so I'm not going to show any of this, but in regions where you've got strong nudging, you can look at dominant momentum balances and at least speculate on which process is, well, the one that you want to look at in terms of parameterizations. Okay, so back to the nudging. So here, I'm just showing the low-level nudging that's required to keep CAM6 close to reanalyses. And so this is a variable on the upper right that I'm plotting. It's essentially just the wind at a particular level, or sorry, it's the nudging at a particular level dotted with a unit vector in the direction of the wind at that level. And then there's this vertical average that's density weighted. And then these brackets are time average. So the time average is just 2009 DJF. And then the levels that I'm looking at here are just the lowest 3 levels. So these are the nudgings vertically averaged over the lowest 3 levels in the direction of the wind required to keep CAM6 close to error interim. So on the left-hand side, this is CAM6 nudge to error interim. Middle is the CAM6 UW nudge to error interim. And then the right-hand side is CAM6 minus CAM6 UW, just the difference of these two. I guess the big result that, a big thing that I see in these plots is that overall, especially in CAM6, more low-level drag is needed really in both of these configurations in order to keep CAM6 close to error interim. So if you believe error interim, over the ocean, over, much of the world, more drag at the lowest levels would potentially improve simulations. And then comparing, CAM6 club to CAM6 UW, more nudging is required in the default CAM6 than CAM6 UW. Don't have an explanation, but that's just a quick comparison. Okay, so it seems that there's too little low-level drag, at the lowest three levels. Well, this could be an issue with a vertical redistribution of momentum, or it could be a surface stress issue. And so to kind of figure out whether or not it's one or the other, I did a quick analysis. Sorry, my puppy's whining in the background. I did a quick analysis of the vertically integrated momentum budget. And so here's that momentum budget again. Here's all the different parameterization terms. If you assume all of these terms that influence the horizontal momentum essentially have this form of this momentum flux divergence, and if you define this vertical integral from the surface to the domain top, this vertical integral will cause all of the terms that only redistribute momentum in the vertical to be zero. And so you only left with terms that have, a momentum flux at the top or bottom. Well, the terms that do are, that due to surface friction, there's the Béliards and orographic gravity wave drag. And those terms, by and large have a flux at the bottom and nothing at the top. So your momentum budget vertically integrated looks like this. And if you go over the ocean where there's no terrain, it's simple. There's this four terms. There's the total tendency, dichord tendencies, vertically integrated. Then there's this surface stress term due to surface friction. And then there's the nudging. And so once again, if you were to assume that the UDT and the dichord tendencies are correct in these nudging simulations, then the vertical integral of your nudging tendencies would be a surface stress error. So what do we see? Ideally, so here I'm looking at the vertically integrated nudging tendencies in the direction of the wind on the lowest model level. So I guess you'd really hope that these terms would be essentially zero. And then you could state that, well, it's not a surface stress issue. This low level nudging, club would be the parameterization to focus on, or the process to focus on. But that's not the case. So I guess I'll just quickly state that, if there's a particularly problematic area, we'd have to probably look at both club and surface stresses, but we'll come back to that eventually. Okay, so I've said multiple times, let's see, what time am I at? How much time do I have left?
Let's see. You are 11 minutes in of 15, including questions.
Sure. So just one quick little section, I've stated multiple times that, in these nudging simulations, we were kind of assuming from the start that the time tendency and the dichord tendencies are correct, and then that allows you to interpret nudging tendencies as total physics errors. But is this actually the case? One way that we're looking at this is, well, we have these two different configurations of CAM nudged to the same analysis. The dichord doesn't change. You hope that the state doesn't change all that much, and so your dichord tendencies, you hope, would be kind of constant. And then, differences in nudging could be attributed entirely to differences in physics. But so here's all of those four terms. I guess all I really wanted to point out was that if you look at these dicor tendencies, here's CAM6 default nudge to error interim, CAM6 UW also change nudge to error interim. You change the physics, even if you're nudging to the same analysis, you do change the dicor tendencies, unfortunately. And you can see this well, it's really stark in the North Pacific. Don't know what's going on there, but there's subtle differences in the Southern Ocean as well. And so that's kind of problematic. So if you have more or less nudging in one configuration, well, the changes in nudging are due to different physics, but also the state is changing just enough, even in these nudge simulations, that you're changing your dicor tendencies. So that's kind of throwing a wrench in this idea that nudging tendencies can be just interpreted as your total physics error. And I'll just quickly state that Julio and I have been trying to compare an ideal momentum budget to an actual nudge momentum budget and defining a physics error metric, and then using nudge simulations with nudging timescales of 6 hours, which is typical, and 30 minutes, which should really bolt CAM to the analysis. We might be able to, estimate some of, well, this particular physics error metric. So just to summarize, CAM6 with club and the previous UW schemes both require additional drag on the low level flow in order to match both error interim and MERA 2. This missing low level drag, unfortunately, you can't say it's just club or just surface stress. It's probably a combination of both. Changing physics or even the tuning parameters, which I didn't show, changes the dicor tendencies, which throws a wrench in how to interpret, nudging. But we're working on a way to define a physics error that accounts for an interaction of physics and nudging and the dicor tendencies. So I'll stop there.
Okay, that was really nice. Thank you. So we have one question from Yunpeng Shen, who says, nice talk. I wonder, what is the time range of available nudging data from what year to what year?
It depends on the reanalysis, but on the ones that I'm using, it's like, well, satellite era, 1979 to present at a minimum.
Okay. And what years are you using for your actual analysis? All of those?
So not yet. For this stuff, this is just a single DJF. It's December 2008 through February of 2009. We will eventually do at least a 5-year nudge simulation and, average over, particular season and those 5 years. But that's what we're working on right now in order to sort out like what nudging timescale to use, what nudging algorithm to use, and gain confidence in these metrics.
Okay, sounds good. And Isla asks another question, but I think in the interest of time, let's move on and hopefully you can answer that in the chat. Sure. So next, Meg Fowler.
Great. Let's see if I can share. Okay, can you all see that?
Looks great, thanks.
Awesome. Thank you. So my name is Meg Fowler. I'm a project scientist here at NCAR and CGD. And I want to talk just a little bit about some work I've been doing looking at the connections between club's higher order moments and the surface, and in particular the land surface. And I'll acknowledge my co-authors, Rich, Dave, Nate Cheney, Meng Wang, and John Truestill have all contributed quite a bit to this project, just part of the class CPT, but this list is by no means exhaustive. So I want to start really broadly by thinking about this background picture in a little bit more detail, because I think it illustrates kind of nicely that in reality, in the real world, not looking at models, there's a pretty tight interaction between the land and the atmosphere, and it can occur on pretty small scales. You can imagine there's differences in sunny and shade-lit areas in terms of surface fluxes, surface temperatures, humidity. But on the land side, all these different land surface types, different crops, grassland area, forests, those can all also impact what we see happen in the atmosphere. So from the land, that surface heterogeneity here in plant types and land cover can really matter. land surface heterogeneity has been linked to influences on cloud development, deep convection, and even just general boundary layer interactions that we can expect to occur. And of course, coupled models can't always perfectly represent these small scale interactions. So in CESM right now, CLM5 represents a lot of these different land surface types. So within a 1 degree grid cell, you could have, say, urban area, grassland, forest, and cropland. But all that gets passed up from CLM to the atmosphere is just a grid cell mean. And so the atmosphere has no idea that there are all these different land surface types. Similarly for the atmosphere, although we do have subgrid heterogeneity there now in terms of club and the variances and covariances that it represents, that is also not communicated down to CLM. And so the reality is that we're dealing in grid cell means when we actually have more information than that available to us. And so it's sort of what this CLASP CPT is trying to address, where CLASP stands for the coupling of land and atmospheric subgrid parameterizations. This is a multi-institutional effort. But from NCAR's perspective right now, our current goal is to figure out how we can communicate subgrid heterogeneity that exists in CLM, those different land surface types, up to CAM. And so one of the ways that we're looking at possibly doing this is by using the high order moments that CLUB computes at the surface and moving that calculation out of the atmospheric model into the land model. And one of the motivations for doing this is there's a kind of nice methodology laid out in Malchowskaya and Mironov in 2018 that can kind of walk us through how to do this. So if you think about a grid cell from the land perspective, you may have two different land surface types, which we'll refer to as tiles. One may be urban and vegetated. And when communicating things like fluxes up to the atmosphere, what we've been doing is just passing up the grid cell mean, as I mentioned before. And so if we were to compute those higher order moments for club, the variances and covariances, the old method would be just compute the grid cell mean and pass that. What we want to do, though, is account for the fact that the grid cell mean doesn't actually tell you what's happening in either of these tiles. They're pretty different from that. And so can we account for that variance that occurs between the tile means and the grid cell mean? So one of the ways that we can look at this and kind of start to assess what impact that might have on the atmosphere itself is through a series of single column scan simulations. We've run these so far for 1 month, June of 2015 at the Southern Great Plains ARM site. And we're running this with 64 vertical levels rather than the default 32 that CAM-6 kind of relies on to better represent the boundary layer itself. Now we have two different experiments. The homogeneous case, again, is going to assume that we're just computing grid cell means of these higher order moments in clubs, so kind of this green bar here. The heterogeneous case accounts for that subgrid variability that happens across tiles. And so we have these moments that were computed based on an offline hydroblocks run from Nate Cheney over at Duke. So I will note that this is not CLM driven, so it's a little bit of an ad hoc approach. But this way we can actually look at, if we prescribe those higher order moments at the surface, the variances and covariances between temperature, humidity, and velocity, and we prescribe those to CAM, what happens? And so if we average over, say, the entire month of June, and we look at the boundary layer height, what you'll notice is that the heterogeneous case here in blue starts to evolve a little bit differently than the homogeneous case in red. And so you're peaking at a lower height overall. What's also interesting to note is that that effect doesn't necessarily occur equally at all times. This is a bit more complex than that. And so if we look at the month of June and we kind of split it up into 3 periods, in the middle of June, we have pretty frequent precipitation. And during that wet period, the differences between the heterogeneous and homogeneous case in terms of boundary layer evolution aren't necessarily that dramatic, but you do really start to notice them during the drier periods. We can also dig a bit further down beneath this and try and figure out, well, what is driving that difference in boundary layer evolution. So the previous plot that I showed you, we were prescribing all the surface moments at once. So the 15 or so variances and covariances that CLUB uses, but they don't all necessarily contribute equally to this. And so what we've done is a set of 3 different sensitivity experiments, prescribing just one moment at a time. So prescribing the variance of vertical velocity, W prime squared, the variance of temperature, or the variance of moisture. And if we look again at the difference in how the boundary layer height evolves over time, it's really that by prescribing the variance of temperature in particular at the surface, you start to see those really noticeable differences that occur by just having heterogeneity represented at the land surface. And what's interesting is that prescribing temperature variance at the surface does more than just change that one field, obviously. And so here at the surface, this is the temperature variance time series over the first 11 days or so in June, so that early dry period. And so just to get a sense of the scale of these differences, we are bumping up the temperature variance quite a bit relative to the homogeneous case. If we look at averaging, again, over that early dry period, the temperature variance difference between these heterogeneous and homogeneous cases really is emphasized here in the afternoon and early evening hours, and extends a bit above the surface as well. So it's not happening exclusively at the surface. It does extend higher up. It's also not confined to just one field. And so again, if we look at the differences here between the heterogeneous and homogeneous cases, you'll note that in the difference for specific humidity, you can see the boundary layer height is a bit lower. You tend to get a little bit more moisture here at the surface. And although we are increasing the temperature variance, the liquid water potential temperature itself has actually decreased a little bit in this heterogeneous case, which is really noticeable overnight, so more nocturnal of a signal. What's also, I think, really interesting is that we're prescribing the temperature variance, but all those other moments, Club is welcome to evolve as it sees fit. And so even though in this case we aren't prescribing the vertical velocity variance, we are still seeing a signal in that variable. And so you're getting this overall decrease in vertical velocity variance when you apply heterogeneous land surface conditions rather than homogeneous ones. And so I'll wrap up kind of the first half of my talk on that just by stating really broadly, land heterogeneity can have really big impacts on the near surface atmosphere. They extend above the surface into the boundary layer itself and aren't necessarily distributed evenly in time. There is, of course, ongoing work on this as part of the CPT. Here we're looking at how to integrate this into a CLM module, compute the surface moments of Club there, pass them back up, and then look at the impacts on the atmosphere at regional and global scales using more of a consistent CESM framework. And I'd like to also shift gears a little bit and kind of do a 180 because there's two sides to this coin of heterogeneity, right? We have what happens on the land surface with all these different tiles. But in the atmosphere, Club gives us information at the subgrid scale as well. And so what we're wondering and starting to look at is, can we leverage the information in Club on those variances and covariances of temperature, moisture, and velocity and improve what happens at the surface? And so if we think about surface fluxes, we know that there are biases in these around the world at different magnitudes and scales. So here we're looking at a comparison between a long-running CESM2 simulation and reanalysis on an annual timescale. And what you'll notice is that there are pretty large biases in different portions of the world. Some over land for sensible heat flux are super noticeable, but especially in latent heat flux. We're also interested in looking at how ocean fluxes are being impacted. And so what we are trying to think of is can we say more about where and when those biases and fluxes are most pronounced? So not just looking at an annual scale globally, but really trying to drill down and understand this in more detail. So right now what we're doing is comparing a long-running AMIP run against observations from about 115 FluxNet towers, which I've plotted here. Each of these towers has at least 5 years of data to compare against, and so we're using as much of a time series as we can from each of these stations and comparing against 2000, 2014 of model simulation. And just super preliminary kind of results of what we're looking at. One question was, what does the presence of rain do for the bias magnitude in terms of surface fluxes? And so what I've done is in both the FluxNet observations and in CAM-6 AMIP simulation, kind of binning days that have rainfall falling in these different amounts here, as you can see on the bottom, the x-axis of this figure. And looking, if we average over all of those days and over these 115 stations or so, what do we see happening? And so you can notice that in terms of the latent heat flux bias and the sensible heat flux bias, as you do move to these higher rain bins, you start to see that the bias overall is increasing a little bit. For evaporative fraction, that signal isn't necessarily as strong. So evaporative fraction is the ratio of latent heating to the sum of sensible and latent heating at the surface. So how much of your flux is going into evaporating. The biases overall aren't too bad. I will note these are not sensible and latent heat flux in watts per meter squared, but EF is just a fraction. But the largest fraction seems to be occurring at lower rain rates, not at the higher ones. I will note, though, that if you were to break this down seasonally, this pattern of increasing flux biases is pretty consistent for sensible and latent heat flux across seasons. not necessarily as much so for evaporative fraction. So maybe a bit more noise there to be assessed. But just to say that, there are kind of these two sides of the coin where our ultimate goal across numerous projects is to figure out how we can communicate subgrid heterogeneity between the atmosphere and the surface in both directions, ideally to improve our simulations. So with that, I'm hoping there's time for questions, but feel free to reach out via email if not. Thanks.
Yeah, that was perfect timing. Thank you for that. So we have 3 minutes for questions. And I don't think I see any on the chat so far. I had one question, which is, do you think that the computational cost of adding this subgrid information back and forth is going to be negligible, or is it going to be sizable?
Yeah, that's a good question. And none of us have really gotten the chance to address that yet on the CPT. My hope is that it shouldn't be dramatically more. We are moving this calculation into the land model, and so we might see a small uptick there, but I don't think it would be significant compared to changing vertical resolution or anything like that.
Great, thanks. Seems like a good idea. And we have a question in the chat. I'm going to read out from, I'm going to get the name wrong, Senlin He. And so Senlin says, nice talk in your comparison between CAM6 and FluxNet. Did you run coupled global simulations or point scale column simulations at site locations? If the former, the subgrid heterogeneity could affect your comparison.
Yeah, that's a great question. So these are actually just AMIP simulations, so not necessarily fully coupled, nor are they single column simulations. What I did was just kind of take existing output we have from long running CESM2 simulation and kind of pick out whichever grid cell has that FluxNet tower. So it's absolutely not as perfect as it could be. And I agree, there's probably more refined ways we could do this. Yeah, but we haven't gotten there just yet.
Okay, and Julio asks the question, has class considered coupling subgrid land to the schemes, e.g. ZM or deep convection?
So yeah, in terms of like coupling outside of the club moments.
Right.
Yeah, so not the part that I'm most involved with. I'm mostly working on the club side, but I know that there is work in class looking at how to do this with EDMF as well, if I recall right. I don't know that there's an extension to look at the deep convective scheme, but it is it's all in development. That might be something worth looking at.
Great. Seems like a great project. So, okay, let's move on. So Ben Stevens.
Okay, I'm gonna share my screen. And
that looks perfect.
Am I good?
Yep, looks great.
Okay. Hi, I'm Ben Stevens. I'm a postdoc with Vince Larson at UW Milwaukee. And I'm going to present some work we've been doing trying to improve club's modeling of subcloud vertical velocity skewness. So as a unified parameterization of turbulence and clouds, club avoids some of the difficulties of understanding interactions between different parameterization schemes, but one of the challenges is to accurately represent the skewness of the vertical velocity. And for the purposes of this talk, probably it's enough to understand that skewness we expect to tell us something about the cloud regime. So a large skewness would mean sort of like a few strong updrafts, whereas a small skewness would correspond to sort of roughly equal likelihood of updrafts and downdrafts, sort of like in a stratocumulus layer. Now, I'm not going to refer to the skewness per se in the talk. I'm mostly going to refer to W prime cubed or WP3, which is closely related to skewness, as you can see from this equation here. It's just the horizontal mean, basically, of the cubed vertical velocity perturbation, W prime. So the basic problem behind this talk is that LES results show a subcloud peak in WP3, which doesn't show up in club. So what you're seeing here are some SAM LES results for the BOMEX cumulus case above and the DICOM's stratocumulus case below. And in these left plots, I've indicated there's this subcloud peak in both cases. To learn something about where this is coming from in SAM, we can look at the budgets for this quantity. And we do see, well, we're trying to understand this in more detail, but our sort of working hypothesis is that this positive contribution near the surface from pressure, that's the orange line in both cases, is through a feedback is sort of being amplified by buoyancy, which is the green line, which we think is what's corresponding to this subcloud peak. Club should mimic this behavior, but we're not seeing that in the default configuration that we're using. So these are for the same two cases, BOMEX and DICOMs, same plots pretty much except for club. So on the left, we see the black line for SAM LES, and then the red line is the line for club, which, as you can see, doesn't show the subcloud peak. So we can look at the budgets for club, and we notice that there is no positive contribution from pressure near the surface in either case. Those would be the orange and brown lines in club. And furthermore, there is no bump in this gray buoyant production term in club like there is from the LES. So we think this is basically coming from two problems. One is the way that, so basically club's standard pressure terms are not really capable of producing a positive contribution from pressure near the surface. So this is the equation for the time evolution of WP3, or at least the dominant terms of it, which are labeled here on the left. But if we look at the pressure terms, PR1 and PR2, these are usually going to damp WP3, but if WP3 is initialized at 0, which it typically is in club, then these terms are actually all going to be 0 to begin with. So they're just not going to be capable of generating a positive W prime cubed. So that's the first issue that we see. And then the second problem is that club's buoyancy term alone really can only amplify existing WP3. So this term on the left here is the term from that equation I just showed you this is the buoyant production term. And this is closed using club's subgrid PDF, which means that it ends up being, it ends up looking like this term on the right with the W prime cubed in it. So again, if W prime cubed is 0, then this isn't going to help us. You may notice that the virtual potential temperature is here on the left and the liquid water potential temperature is here on the right, but these are going to be equal in a subcloud layer with W prime cubed equals 0 in club. Okay, so the basic idea is we think there's some missing physics here, and we need a new pressure term in the WP3 equation in order to reproduce what we see in the LES. So we came up with an idea that's based on something we noticed in some papers from a couple of years ago, 2015 and 2016, by the authors at the bottom of this slide. In the 2015 paper, they had some plots of BOMEX on the left and DICOMs on the right for the turbulent kinetic energy, or TKE. And then the next year, in the 2016 paper, they had a similar plot for the standard deviation of the pressure perturbation, P prime. And we noticed the similarity in these plots, and we thought we could make use of this similarity using the generic form of the pressure term from the WP3 equation. So if you derive the WP3 equation, it will, the unclosed form of it will have this pressure term in it, which contains the vertical derivative of P prime. Now, we don't have P prime in club, but we do have TKE. So if we can make a correspondence between P prime and TKE, then we may be able to take advantage of the fact that there's likely going to be a negative gradient here near the surface in TKE, and combine that with this minus sign, we can maybe get a positive contribution to WP3 even in the absence of WP3. So we tried to implement this. So this is the basic idea. We assume that P prime is proportional to the density times the turbulent kinetic energy. And we take the generic form of that pressure term and replace P prime with rho times E. And then we can put a tunable parameter in front, which I'm just calling C turb here. And we can add this onto the time evolution equation for WP3. So obviously C turb equals 0 would just bring us back to the default case, but a non-zero C turb, we can experiment with this new term. And results have been encouraging. I'm sorry. How do I get rid of this? Sorry about that.
Yeah, we can't see it. If you can just move it out of your way, we're good.
Oh, okay. Okay. So so results are encouraging. So this is for the BOMEX case. So on the left-hand side, this is the same plot I showed before with the SAM LES line and then the default line for club. When we set C turb equal to 1, we get this blue profile, which as you can see has this subcloud bump, similar to what we see in the LES. And some other quantities can be improved as well doing this. So I'm showing you the time series for the liquid water path here, which not only doesn't have these big oscillations that we saw in the default case, but stays closer to the LES line. And then to give a sense of the workings of this term, I'm including the budget plot for this new case. I am zooming in here on the subcloud layer, so the range is different from this plot on the left. But basically, if I look closely at the subcloud layer, this red dashed line represents the effect of the new term. This is the positive pressure contribution that we've been trying to include, and then the gray line is the buoyant production term, which we think is acting the way we were hoping it would. It's basically amplifying this positive pressure contribution. And then similar kinds of improvements in the DICOM's case. This blue line here, of course, certainly has a better shape now than it did before. And then liquid water path again seems to stay a little closer to the LES line. And then again, with the budget plot, we see an improvement in, well, we see that again, the red dashed line has a positive pressure contribution from the near the surface. And then the gray buoyant production term is there now too, which we think corresponds to this peak over here. So just to sum up, we think that there's some missing physics in club, and we need this additional term to reproduce what we're seeing in the LES with this near surface positive contribution from pressure. And we make use of a similarity that shows up in LES between TKE and P prime to construct that term, and it shows some improvements. And as far as ongoing work, it's sort of more on the theoretical side. I guess we're trying to better understand the link between the positive pressure and the buoyancy in LES. And we'd like to offer, I think, a more satisfying sort of theoretical justification for the new term. And that's it. So if there's time, I can take questions.
Okay, thanks. That was a great talk. I don't see any questions in the chat, but I had a question about, have you created scatter plots or in any way done a better job of quantifying how good TKE is as a proxy for the standard deviation of P prime?
No, we haven't. We probably should explore that more broadly, of course. Mostly, we've just been looking at a few of the standard club test cases so far. Yeah.
Mm-hmm. Okay, thanks.
Mm-hmm.
Sorry. So not seeing any other questions right now. I think maybe we should move on to Ji Zhao.
Yeah. So am I visible?
Yes, you are. So, yep. And you sound kind of quiet. I don't know if you can get closer to the microphone or something like that.
Sorry.
If not, we can turn up our volume a bit.
Okay, can you hear me now?
I can. It's still a little bit quiet, but I think it's great. Let's go for it. You're not sharing your screen anymore, it looks like.
Okay. Okay, can you see me now? Okay.
Yes, it's great. Thanks.
Thanks. Hello, everyone. My name is Ji Zhao. Today, I'm going to be talking about the representation of secondary ice production in the CAM-6 and also its global importance. First, I would like to acknowledge my grade advisor, Dr. Xiaohong Liu, co-author Wen Finks and Shashin Patade. We also like to acknowledge my Meng Zhang and Grandma Fakwa for their help with the observation data. So this is the outline of my talk. First, I'm going to talking about the background and motivation, why we need to add the secondary ice production into the global model, why this process is important. Second, I will move on to the method part, what we added into the global model, and then we focus on the model simulation result. So now let's begin with the motivation. As we show in this figure, the dots is the ice number concentration from the observation. The line is the observed IMP number concentration. As we show in this figure, the measured ice number concentration is orders of magnitude greater than the IMP number concentration, indicating that there must be some process happen after the primary ice nucleation to produce enough ice number concentration. We call this process as the secondary ice production to differ from the primary ice nucleation process. As we show in this figure, the secondary ice production process is very important to produce enough ice number concentration in the nature cloud. Okay, our second motivation is we notice a high climate equilibrium sensitivity in the CESM2 model. Currently, is 5K. Previous study indicating that once the liquid fraction in the cloud increase, the equilibrium climate sensitivity will increase accordingly. So we think the high climate sensitivity in the current model is related to the liquid dominant cloud phase scenario. A lot of physical process contributed to the liquid dominant cloud phase, and we think making a comprehensive representation of SIP process in the model is also an important reason. So to summarize my motivation is, we notice that in the observation data, the secondary ice production process is very important to produce enough ice number concentration. But those processes is highly simplified in the current model, which will result in high climate sensitivity. So our work is trying to bridge a gap between the observation and also the model. What we do is added a comprehensive representation of secondary ice production process into the climate model. Okay, so generally, there are 4 different types of secondary ice production process in the nature. The first process is called rhyming splinter, which is already added into the microphysical scheme in the CAM-6. The second process is called ice-ice collision fragmentation, as shown in this figure. The third process is the droplet shattering and the sublimation fragmentation. Our work is to add the ice-ice collision fragmentation and the droplet shattering process into the current model. Unfortunately, there is no mature parameterization for the sublimation fragmentation process, so we cannot add it into the model. So after we implement those two processes into the climate model, we do two simulations. The first simulation is control simulation, use the default CESM CAM-6 model, which only considering the rhyming splintering. The second simulation is called SIP, which considering the rhyming splintering, ice-ice collision fragmentation, and also the reinforcing fragmentation into the macrophysical scheme. Now we move on to the model result part. First, I will show you the single column model result. We focus on the M-PACE campaign, which is happening in the Arctic region during the autumn, and then we move on to the global model result. Now we begin with the single column model result. This figure showing the cloud face. The x-axis is the liquid fraction. The y-axis is the altitude in the cloud. The first figure is the observation. The second figure is the control simulation. The third figure is the SIP simulation result. As we notice that in the observation, the mixed phase cloud occur in all altitude in the cloud and is dominant over the bottom of the cloud. From this table, we also notice that the mixed phase cloud occurrence is 62%, but it is only 26% in the control simulation. As we shown in the figure B, most of the cloud is a pure liquid phase cloud in the control simulation. When we look at the figure C, the SIP simulation result, we notice that the mixed phase cloud is increased significantly after we have the secondary ice production process in the model, which is much more similar to the observation. And the mixed phase cloud occurrence is increased from 26 to the 58% in the SIP simulation. So we conclude that after the model has the SIP process, the model will have more mixed phase cloud and less pure liquid phase cloud. This figure showing the ice spectrum. The x-axis is the ice number concentration. The y-axis is the possibility occurrence. The green line is the observation, the orange line is the control simulation. The green line is the SIP simulation. We notice that after the model has the SIP process, that's the green line. The spectrum showing a rightward shift with a longer and broader tail, which means we have a higher ice number concentration in the cloud now. So this is the single column model result. I will move on to the global model result now. I think the most important and interesting question you're going to ask me is the relative importance between the primary ice nucleation and the secondary ice production. Which process is more important? This figure showing you the global vertical distribution of the secondary ice production rate, that's a figure A. Primary ice production rate, that's a figure B. And the relative importance between the secondary and primary, that's a figure C. The red color indicating that the secondary ice production is more important than the primary ice nucleation if the color become more red. We notice that the SIP process is spread in the mixed phase cloud and is dominant over the South Ocean in the moderately cold cloud. This figure showing you the global annual mean zonal distribution of the liquid water path in figure A, ice water path in figure B, and also the cloud forcing. Note that the green line is the observation data. The green line is the observation, the green line is the SIP simulation, and the orange line is the control simulation. We notice that after the model have the SIP process, the liquid water path decreased significantly in the mean latitude and high latitude region in both hemispheres, and the ice water path increased significantly in all latitude. And the liquid water path and ice water path is much more, it get a better agreement with the observation data. That's the green line. This table summarizes the global annual mean, long-wave cloud forcing, short-wave cloud forcing, net wave cloud forcing, and also the cloud water path. As we notice that the liquid water path decreased 20%, while the ice water path increased 20%. We also get a weaker cloud forcing. The net cloud forcing is weaker by 1 volt per square meter from a global annual mean perspective. So to summarize my work is we added 2 new SIP mechanisms in the CAM-6 model, which is the ice-ice collision fragmentation and also the ruin-freezing fragmentation. Our single column model results showing that the SIP process significantly changes the cloud phase. Our model will have more mixed phase cloud and less pure liquid phase cloud after we have the SIP process. The ice number spectrum showing a rightward shift with a longer and broader tail, indicating a higher ice number concentration in the cloud. The global model results showing that the SIP process is dominant over the South Ocean, especially in the moderate cold cloud. And the liquid water path decreased 20%, while the ice water path increased 20%, with a totally weaker net cloud forcing by 1.1 volt per square meter. We expected a decrease of climate sensitivity resulting from the change of the cloud phase in the model. So that's my presentation. Thank you for your attention.
Thanks, that's very nice. So let's see. I don't think that we have any questions in the chat yet. I had the question of, so you included some secondary ice processes, but noted that you're not including others. Do you have any theoretical expectation of whether the processes you're not including are going to have a big impact, or do you think that they're relatively secondary?
Generally, we have 4 different types. The Ramin splinter is already added to the model. We added 2 additional processes, ice-ice collision and droplet shattering. The first process we didn't add it because there is no parameterization for this process. But I expected this process, the ice-ice collision fragmentation is the most important process. This process may have some influence, but is not the dominant process of the SIP.
Okay, great. Thanks. That's a great explanation. Okay, I don't think we have any other questions at this time, so let's move on to Rich Neal.
All right, can you hear me?
We can hear you, yep.
Good, all right. Hopefully I can do the share without messing up. How's that look?
Looks great. Off you go.
All right. So yeah, this is going to be a little bit of a hybrid talk in terms of just looking at some aspects of variability and some aspects of the physics and physics tendencies. So it's tropical wave variability over South America. And just a couple of like groups of motivations. Recently, we've committed to doing a super high resolution version of CSM for our South American affinity group at NCAR. And we know that a lot of wave activity, as I'll show soon, is kind of intimately related to a lot of the tropical climate and weather extremes experienced there. And it's just part of the larger landscape of convective variability that it kind of forms part of. And out of interest, it is less studied than other regions, and yet it is the region of the strongest Kelvin wave activity in the tropics. Now, specifically, we're going to look at how CSM sustains these wave activity, if at all, and pushing towards the physics, try and understand what the consequence of interaction with the Andes are. And as part of that, we'll take a look at increased resolution and some aspects of resolving convection explicitly. So South American precip climatology, DGF, we can see that when we compare CAM-6 on the right there, so AMIP simulations with TRIM on the left, a number of differences you notice. The first one that, that is the kind of primary bias in this region and other orographic regions is the high precip right on the top of the mountains on the Andes that just does not exist in observation. So that's a kind of big bias we need to look into. And so we'll be looking at a number of AMIP simulations, most primarily CAM-6, and trying to answer the questions: how is it locked to high topography? It reproduces ITCZ features pretty well. You can look there as this kind of dominant southeast-northwest maxima is not too bad. Too far north, and then there's also the dry tongue right along the Andes, which is probably associated with the maxima over the mountains. Linking is kind of variability. This is the same, but for just straight unfiltered daily variability, standard deviation. And so you can see, also the mountains, the Andes really pop up in terms of high variance, so high mean, high daily variance. But also in the interior of South America, it's very much weaker than TRIM. So it's like the question we're asking is, can we identify the source of this variability weakness? Is it this tropical wave variability? And when I talk about tropical waves, there are kind of three that are types that are observed to influence northern South America. The first is a non-local, equatorially confined, tropical equatorially confined Kelvin wave. And that, in essence, propagates from well, not necessarily, it's local, and it propagates from the central and western Pacific and leads to precipitation anomalies over South America. The second version is actually the MGO, so the Madden June Oscillation, this much larger global tropics-wide scale disturbance that exists, propagates over South America, but it really, the key thing is that within that propagation, there is these embedded Kelvin waves. So that's the kind of second source of Kelvin waves. And you can see in this bottom right here that, the strength of the Kelvin wave we can see is in the red there. So it's covered up in, And so when the MGO is a maximum early on and really late on, then the maximum of the Kelvin wave envelope increases. So that's in that second type of wave. The third type, not really going to talk about that much, but that's a high latitude forced type wave. So these trough systems make their way poleward from around Argentina northward to impact the tropics over a few days. So what do they look like? And so I'll show you a couple of plots here. And this is essentially, TRIM on the left-hand side, CAM-6 on the right. And we're looking at the precipitation anomalies for a winter, 2001, 2002, within the tropic envelope, tropic region. And so if you look at the raw fields, you can pick out a few types of kind of variability, and you can superimpose, you know, modal types of waves. Let's show here MGO, Kelvin, equatorial, as we inertial. And so there's a lot of activity going on. It's very busy. A lot of things can be described as a mode. So I'll filter out and just leave the blue, which is the Kelvin waves, and the MGO, which is the black, which is the MGO. So we can see both locally and non-locally, there's an impact on South America between the two green lines. It does look weaker in CAM6 versus TRIM. If you look at the bottom right there, the variance explained is shown there. And of course, it's hugely different in TRIM versus CAM6. So there's a real deficit. You know, it kind of makes you think that, you know, the reduction in the variance that I showed to start off with is due to this wave activity. So I want to, in terms of thinking about these high resolution experiments we were to do with CSM as part of this water cycle activity, I want to do essentially two sets of sensitivity experiments. I only have them with CAM5 for higher resolution, so I'm going to show CAM5, which actually is a little bit weaker than CAM6, but I think the story is pretty much the same. So here, we're looking at standard deviation, TRIM, and top right, a low resolution standard CAM5. And now on the bottom left, we're turning off deconvection. Many people do this, but this is kind of a seed for what will happen in these high resolution simulations. We turn off deconvection. And then the bottom right is actually a high resolution version, but with deconvection maintained. So as you can see, the variance is much higher and it's in more keeping with observation. So the bottom left and right. And so the impact of kind of turning off deconvection, bottom left and bottom right, increasing the resolution is about the same. The big thing that sticks out is the Andes maxima just kind of goes, you know, off the roof. And so does this represent a problem for tropical wave activity? Yeah, so can we relate any kind of wave activity problems to this? So just to kind of take a sidestep for this is kind of giving you an idea what's going on over the Andes. So these are slices, east-west slices. This is just the CAM6 kind of preset here. But east-west slices average for 10-degree segments. So this is 30 south to 20 south, and so this bottom piece here. And so you can see that over the Andes, we're showing the actual all moist processes, the tendencies from all moist processes. And you can see, you know, in all these cases, low res, high res, no convection, it is fixated. It is fixed on top of the orography, and that's anomalous. That's a big bias. It's enormously bad. And there is some convection over the rest of South America. And we can move forward to this next segment where this maximum precip actually is. And we can see that, you know, the biases are even stronger, you know, as it shows from the precipitation on the whole in CAM6. But in general, you know, no convection there really is giving rise to a lot of an excess precip and very strong contributions, obviously, from physical processes. The high res, you know, you'd start to think, well, maybe that's defining the orography a little bit better, or the problem may even get worse, but it's about the same for this particular metric. And so it's not off the charts that you're forcing the problem much strongly at high resolution. And then really in our region of interest is in this tropical belt. And now it kind of merges with the kind of distribution of these tendencies merge with the central South America. But it's still, I mean, it's still, you know, a local, well, it's on the periphery, it is a maxima over the Andes here. And so CAM5, as we know, top right is a little bit weaker. And so in CAM5 high res and CAM5 no convection here, it's really locked as a local maxima. So that kind of makes you ask the question, is that a problem for wave propagation if it's just locking to the convection potentially? But just one piece in between before I break that down a little bit. Here we can show, like, what is the contribution? I think Julio has shown in the past that, you know, convection, but physical processes over the Andes are really excessive. And the question is, what's the breakdown of that? Now, this is just, yes, flipping a little bit here, but CAM6 default 1 degree. This is the repeat of the all moist And again, this is this tropical kind of latitude belt. And so if we were to break it down into the two primary physical packages in CAM6, we can see that deep actually is not that deep. Deep is shallow compared to the moist, and then club is deep. So there's a certain kind of irony to that, but yeah, club is a local moist turbulent scheme. It's not ostensibly a boundary layer scheme, but it is interesting that that for CAM5 this is much deeper, and the large scale macrophysics in CAM5 does not operate as strongly. And if we were to look further south, actually, club then does really dominate this peak over the South America. So in the last couple of minutes, what happens if, high res versus low res in terms of wave activity? Not a lot. It's quite similar. High resolution doesn't look that exciting. There is some smaller scale features that may give you a sense that the variance is increasing, but it's not a huge difference from low res. But if you turn off the deconvection, in some ways, this is not a surprise. You get a plethora of wave activity. Now, the variance is known to go up in no convection simulations, but this is kind of saying that that variance projects onto these modes of variability. And if we look at now, if we look at these, the variance kind of not explained, but the actual mean variance from these modes, you can see quite clearly that it looks better compared to trim. So clearly the aspects of the locking of the mean precip to the Andes is not an impediment to the wave variability, either occurring over South America or traversing the Andes here. So I have one more kind of plots, and that I haven't really talked about the MGO, but here's an example of the response of the MGO here in a similar way, trying to examine the propagation of the MGO mode across this region. So these essentially, just for the reanalysis, ear interim and CAM5, anomalous composites that propagate past the South America. And these are the two weakest, two negative phase, sorry, and the two positive phase. So basically, if you compare that to CAM5, clearly, the phase, the composite within CAM5 is heavily coupled, associated with the orography. And it's hard to tell with these arrows, but if you look at actually these eastward and easterly and westerly anomalous winds, they just do not care in this anomalous sense about the presence of the orography and go straight over. Whereas in the observed composite, it really does navigate around, both in, as you can see by these arrows going to the north of the Andes. So it really does navigate around. So it really demonstrates that this interaction with the orography, even in these waves, is really important to get the a skillful answer. So that's it. So yeah, I just blew through quickly there a little side project of mine just to look at kind of setting up these South American simulations at high resolution and really looking at these the MGO and Kelvin waves. CAM6 is not too bad. CAM5 is a little worse. We knew that. Clearly is, if anything's to blame, it's the Kelvin wave activity. And so I'll skip that bit there and just go to orography because that's more interesting, and just say, yeah, there are a number of questions. Is it a hydrostatic dynamics problem that is associated with this poor wave activity? But it is this kind of, in some ways, encouraging that we do get an improved activity associated with both increased resolution and turning off convection, which is what we will do with these simulations. Thanks.
Great, nice talk, Rich. So I don't see any questions in the chat yet, so I'll ask my own question, which is, I thought that Julio was saying earlier that he thought that the precip over the Andes was due to not squeezing out enough precip over the Amazon, which he didn't really talk about. So do you think that's part of the issue?
It's, yeah, we could talk about that. I'm not sure I totally agree with that. It's because, I mean, what makes me think that it might not be is you get this trough, let me go back there. You get this trough across the mean precip here, right here, the bottom right. You get this trough of dryness, which to me is responding more to the high precip than it is to what is happening to the east.
Right.
Yeah, I should talk to Julio more, but like I was looking at this recently and thinking that slot of dryness is probably a non-local impact of the convection.
I completely agree with that interpretation, Rich.
Yeah, okay. Good. I'm glad we disagree to agree. It's good.
Sorry for misrepresenting you, Julio. I was just trying to make the conversation more
Peter's
exciting.
just being disruptive. No, that's fine.
Yeah, what I've seen before, and I don't know how it carries over to our latest model, is that by reducing the heating associated with that spurious precip over the end, you do get rid of the dry slot that you see there, and you also get rid of the precipitation over the Andes. But that study basically makes latent heat a function of orography, which obviously can't, even in a GCM can't.
Did you talk about, I mean, Mr. Hula, did you talk about the new stuff that Mark Taylor was talking about in terms of
no, that's a good
fusion
point.
across temperature?
I haven't.
Okay.
That's right. There's new treatments of orographic pressure gradients and things like that might make a difference.
Okay.
Yeah. So Rich, this is Peter. Mark and I have changes that improves this problem with too much lifting over rough orography. And also running physics on a lower resolution grid really helps this problem. And I think that's one thing we'll keep an eye on with comparing all the new die cores is in particular this type of problem. And it will be interesting to see with MPAS that uses a different vertical coordinate compared to the other 3 die cores, what we get over steep, high topography.
I mean, it is quickly, it is interesting because like NGOs, it's most important over the maritime continent, and that has similar problems. So it'd be interesting to see if it traverses that better.
Excellent. Thanks, Peter. That's a good contribution. I'd be curious to see those plots. Okay. I think if there's no other questions, let's go to the last talk of our session, which is Jean Lee.
Can everyone see my screen?
Yep, looks great.
Oh, great. Yeah, thank you. Hi, good afternoon, everyone. So for this presentation, the majority of the work was actually done by my former PhD student, Yi Xuanchen, who graduated last year, and he's working now at the GFDL. You might already heard his name from Jiao's talk about the EMDF because he's the person doing the EMDF work at the GFDL now. And it's also in collaboration with people outside my department, Ping Yang from Texas A&M, and his former student Jiafang Guo, now at Colorado State. And the majority of this work is actually based on a GIL paper we published last year. And probably I do not have time to go over all the details in this 12 minutes talk, and you are welcome to check that paper out, especially the supplementary information has a lot of details of our simulation. So this is the roadmap. I will first define the problem and then talk about why in the traditional climate modeling communities, they take a different approach and what's the traditional wisdom and why the traditional wisdom can break down and when it will break down. And then if we fix this physical representation, what would be the impact on the simulated climate? And at last, I will give some conclusion and outcome. So the take-home message here is just the traditional wisdom of ignoring the long wave scattering, it will break down in the polar region much more than the actual polar region. And the far infrared long wave scattering actually matters more than the mid-infrared. So here is the starting point. So just in reality, if you look at the cloud optical property, let's just focus on this one, which is the single scattering albedo as a function of wave number for different ice particle size and for the liquid water droplet. So as you can see, for some part, for example, around the 400 wave number, the single scattering albedo is as high as 0.85. So even you do a band average here. So each band here is actually the band used in the RTMG long wave scheme. So the single scattering albedo actually can be as high as 0.85. And there is a physics behind it, which is related to the index of refraction. But just to say, it is well established for the ice cloud, the single scattering albedo here can be as high as 0.85. And in contrast, the liquid droplet is not that highly scattering there. Okay. But if you just do a survey for all the CMIP6 or CMIP5 GCMs, there are only 3 out of more than 30 GCMs. There actually assumes the cloud is scattering in the long wave. So over majority of them just assume it's non-scattering. The cloud is purely absorptive in the long wave. And if you look at the CAM-5 documentation, the long wave parameterization just in terms of the cloud emissivity. So there's no way to incorporate the scattering in this framework there. Okay. And just say the GCM has been developed for decades. So such approximation must have a reason there. So don't just brush off, say, it's so contradictory to the reality or the real optical properties there. So 2 factors need to be considered here. It's just say one, the GCM has been developed, especially the radiation scheme has been developed 20 or 30 years ago. The focus is really on the tropics and mid-latitude. The polar region is not that much a focus at that time. And traditionally, when you develop such scheme, you would rather test it first in amipron. And then if the effect is significant, then you'll try to do the integration to see how much it works in the coupled run. So if the polar region was not a focus at that time, you can actually see why the approximation there makes sense to a large extent. Okay, so this is actually related to the water vapor abundance. So what I plot here is just, as you might know, the total column water vapor climatology as a zonal mean there. So globally average is the total column water vapor is about 28 millimeter there. However, if you go to the polar region, let's say if you go to the Antarctic plateau, that will be reduced by almost a factor of 10. Okay. If you go to Antarctic in the summer, that will be reduced by a factor of 3. And if you go to the winter, that again will be reduced by a factor of 5 to 10. And we know the optical depth of water vapor is skewed with its concentration. So the water vapor here will be much, much smaller to here compared in terms of the optical depth. And what really gets into your radiation scheme is not the single scattering albedo of cloud, but it's really the layer average, the single scattering albedo. And we know the water vapor has no scattering, it's just purely absorptive. So that's the reason the single scattering albedo get to your radiation scheme is really this quantity. So if the optical depth of cloud is much larger than the optical depth, the optical depth of water vapor is much larger than the optical depth of cloud, then even your cloud is very shiny, highly reflective. It actually doesn't matter that much. This number will be still small. But however, now if just for exactly the same ice cloud, now you move it from tropics to the polar region, this optical depth of water vapor will be reduced by a factor of 10, for example. Then this number will become not that smaller anymore. And so here I just singled out. So this again is the single scattering albedo for the ice cloud. In this is actually 2 RTMG band. And this band is the bandwidth looks not that much, but the OLR here is actually consists of 30% to 40% of the total OLR. Okay. And there's another aftermath for this small total column vapor in the polar region, which is about the surface emissivity. Due to the time constraint, I will just skip this one, but just say it's actually also makes the case, the surface emissivity also matters more in the polar region than in the extrapolar region. So, okay, and I'll skip this. And on top of above considerations, the seasonality here also matters because this is normally what we have conceptualized in terms of the surface energy budget balance, therefore global average. But in the polar winter, this short term, the short wave term has been gone. All you get balance is really the long wave terms. And then if the scattering can change your downward long wave radiation, that can affect the surface much more than this global average scenario. So in terms of the implementation, we basically replaced the cloud optics in the long wave with the MODIS collection 6 based as cloud optics, which include both absorption and the scattering. And then we have a long wave scattering solver incorporated into the RTMG to do the long wave scattering. And we actually also have some implementation for the surface spectral emissivity, which I actually presented before in the AMWG meeting. And if you're interested, we actually have all the code on GitHub there. So here, what I showed is just a climatology difference from a 4-member ensemble run for the surface air temperature. And you can look at the red curve. That's the difference between the when we turn on the scattering compared to the control run when there's no scattering. Okay. And this is for the DJF.
Is it just me, or did Hong Li freeze?
It seems I'm not sure you can still hear me, or
we can hear you again. Yeah.
Oh, sorry, but it seems my screen frozen. So
great. Okay, is it just your video, or like your webcam, or is it also your ability to change the slides?
I think I also cannot change the slides. So
okay.
Sorry about that.
Do you want to, I don't know, restart your, so maybe we should stop now. You can restart your computer and we'll start the discussion and then you can finish up later. Does that make most sense?
Or you could just try exiting in a full screen mode and going back in and seeing if it.
Kevin's idea is better. Yeah, no.
Yeah, it doesn't work. I think the computer completely frozen here. So sorry about that.
No, that's okay. You're not the only one today.
Okay, I will try to restart my computer now. So.
Okay, sounds good. So
sorry about that.
No problem. Let's see. So let's start talking, and we'll just go back to Hong Li later. So I had 2 questions for this session, which are I guess first, what biases and problems do we think are important to tackle for CAM-7 in terms of the physics? Anyone?
I think it's fair to say that the high climate sensitivity, we're not sure it's a problem. It may be correct. On the other hand, there are some hints that perhaps there is a problem, that the model's too sensitive. I think that is a physics problem that needs to be tackled. I think we've tended to assign that to ice phase microphysics, but I think there may be other parameterizations at play as well, like the boundary layer. I think boundary layer schemes, even though maybe CAM-5 with the same. Well, I'm gonna punt on what the impact of CAM-5 boundary layers on climate sensitivity is. Let me just say that I think we have to consider the possibility it's not as simple as simple ice phase microphysics. There may be more to it, but in any case, I also think it's possible that our sensitivity really is too high.
Mm-hmm.
So, well, I'll let other people talk, but I can make a bunch of comments on that. So you can come back to me. I'd like to hear what other people have to say.
So, I mean, I don't have an answer to this question, but I think that this is a similar question that that I had brought up to Julio after his talk earlier today, which was, there already is, and for good reason, efforts, right, for CES, I keep saying the wrong thing, for CAM-7. And to me, it's just, I guess it's unclear if we've surveyed the community appropriately to know what the focus of CAM-7 biases and improvements should be.
And Kevin, are you specifically talking about the focus in terms of the vertical resolution earlier today? Or?
Well, no, I'm actually talking about, so in Julio's original kind of overview CAM talk, right? He talked about some of the developments for CAM-7, including the boundary layer discussion and some of the discussion we've seen in some of the talks this afternoon. So I mean pretty broad. I mean it very broadly. So I'm not talking about vertical resolution. I'm actually talking about what parameterization should we be targeting. And it seems clear that we're targeting a specific, it's clear which ones we're targeting. I'm just trying to make sure that, are those the right things to be targeting? Because I'll raise up why, I feel like we should be targeting the deep convection scheme more, because it seems to always be the thing that is causing a lot of issues when we go to different resolutions and things like that. And I feel that hasn't been really discussed much. And of course, we're just in day one, so.
So you think the kind of ECS has become kind of, maybe we're focusing too much on that and ignoring other biases that are probably related to the convection scheme, like, other biases we don't understand, like double ITCZ, et cetera.
Right. So, I'll try not to be too provocative, but the ECS thing that we've had a lot of focus on, right? This is in part come from developments and parameterization improvements that went into CAM-6, right? And then once we had a coupled model and we started doing CMIP-6 simulations, we've noticed that there's this pretty large sensitivity. But the reason we started to make those developments for CAM-6 wasn't because of, this climate sensitivity issue, right? It was because of other things that were potentially defined, such as issues in low clouds and things like that were defined as kind of process level things that were the focus, which has now led to something that's now taking a lot of time to focus on. So I'm just wondering, if we do all this development into CAM-7 and we come up, we have a couple extra improvements to the parameterizations, it's possible that just something else will pop up, and then we're going to spend the next 5 years trying to figure out, well, why did CAM-7 do this, instead of actually potentially focusing on, having, I guess, a view of what things we really, really want to improve in the model so that we have a better model.
So Kevin, maybe, go ahead, Peter.
Oh, I was just going to react to that by saying that I feel like there's a kind of a funny tension with, I think if we designed the model development process, we would agree that the thing you do is you figure out what is empirically wrong with your model, like we have too much of a double ITCZ, and then you design parameterizations to try to tackle those specific things. But then in a practical sense, more often, I think you lay in bed at night and you think, aha, I have a new idea for changing how the boundary layer works. And so that's what ends up getting into the model. And so I do think that it's worth coming up with a list of the things that that really bug us about biases right now, and trying to focus on that. I'm not sure if I've seen any evidence of that in terms of the development. That's a rude thing to say, and it's also untrue. Obviously, a lot of the development we've seen today are focused on fixing biases, but are they really targeting the most important biases? I agree that convection's missing more than I would expect. And I'll
say one thing and then I'll be quiet. But I just want to point out that the EDMF CPT is not purely boundary layer. That is playing with a potentially significant change to the models, to the way convection is dealt with in the model. So it's still early days, but that is a potential, that's not specifically that CPT, and actually the momentum CPT too, they're not really specifically targeted at fixing, high latitude ice clouds. there is a somewhat broader, and all the CPTs really, the land CPT as well. There's a broader kind of a broader attack than just focusing on boundary layer clouds at high latitudes or wherever you want.
So I want to react to what Peter and Kevin were saying. There's actually, I think, in thinking about it, there's actually a couple different ways we approach parameterization improvements, and I have more comments that I'll save for a few more minutes on specific parameterization improvements that meet this framework. But we can either focus on biases, which can either be mean state biases, I mean, the things Rich was talking about with precipitation, or they can mean emergent property biases. And by the way, mean state properties could be also like how frequently it rains or the distribution, the higher order moments of it, but it's related to something we can observe in the mean state. Or they can be emergent properties, which I would define as sort of forcing and feedbacks, and biases in how we define that. We can also be focused on developments for physics improvements to meet specific needs. So for example, adding processes because we want to do science piece X, and we've done that over the years with adding aerosol cloud interactions and things like that, and or to meet different scales. So to work across scales, we obviously need to do something about deep convection because right now it's static. It's locked to both the horizontal and vertical resolution in the models we've seen. So we need to do something there. So either of those things are ways that we do model improvement, either to get rid of biases, mean state or emergent properties, which is what Julio was talking about with, say, climate sensitivity, or because we know we want to do a different kind of science with the model, and that's going to push us to do different processes in different ways or more processes. I think those are sort of the frameworks under which almost everything we've seen can kind of be I think that's how they can be defined. I mean, maybe that's a way to kind of look at it and categorize things.
Yeah, I can say something about the cloud phase, and so in the model development and from CAM5 to CAM6 and also other models and modeling centers, like one of the development is to address over the Southern Ocean the cloud bias. In the CMAP5 model, people find out the cloud is not so bright. Maybe there's a large bias in the surface cloud forcing, surface radiation flux of the southern hemisphere. So this is why in the CMAP6 models, so like the modeling center try to correct that bias. So they basically try to increase the cloud liquid, and so at the same time that they try to correct that bias, but the liquid water path also increase over the extropics, so over the high latitude. So this is also increased the climate sensitivity quite a lot from CMAP5 to CMAP6 models. So I was thinking that maybe the modeling center is overcorrected that bias when we introduce the too much liquid. And this is like the process, like how to address the bias, like related to over the high latitude, also related to the mixed phase cloud, so over that region. So the model right now is not just the CAM and other modeling center, they find out the liquid is too much, and so this is one of the phase, too much liquid and too less ice in the cloud.
However, before we go focus on too much on high latitudes, I would like to note some of the nice work that Mark Selink has done, which shows that we know that there should be some more supercooled liquid. So CAM5 is more correct than CAM6. We're just arguing about how much. And I think Mark's work has done a pretty good job of showing with some of the the cloud controlling factors, that it's the shallow clouds, not just the mixed phase clouds throughout the subtropics and the tropics that are somewhat overdone relative to the cloud controlling factors in models like CAM6. I don't think you're wrong, Xiaohong. I do think there are issues with, we've probably gone a little bit too much supercooled liquid. And certainly there are ways that we're looking at now, whether it's secondary ice production or other things in the microphysics, where we're probably going to dial that back as we go forward. But just to say, that's not going to fix our climate sensitivity.
Yeah, we will see how much it changed. Yeah.
if I can make a similar level of a focused point on ECS, I mean, I hear Kevin's sort of, we don't want to turn this into a whack-a-mole due to this natural tension between solving biases and wanting to put cool ideas in the model. But solving the ECS problem, I think, is important. And I'll just say that, yeah, like Mark Zelenko's work, I think, has shown that what we basically, our trade cumulus clouds, the shortwave cloud feedbacks over the trade cumulus regions are just too high, and that maybe in CAM5 they were being compensated. That feedback was sort of being covered up by a stronger ice phase feedback in the Southern Ocean. And so that's an example where when we went to CAM6, we improved the Southern Ocean feedbacks, and as a result, we sort of exposed this trade cumulus feedback. And I hope I'm not getting too much into the weeds here, but I'm getting a little concerned about using club gamma as our main tuning parameter or some club skewness parameter in order to bring our TOA into balance. And I guess I'm a little biased, but I'm advocating for the club MF approach as another way to provide skewness into the model, and also that great talk we saw earlier about assessing skewness pushes us in a direction where we're no longer dependent on these club gamma parameters that I'm afraid are when we start changing them, and all of a sudden the trade cumulus regions are a lot cloudier. Well, that's cloud that could eventually go away when we warm, and so we're impacting our ECS just by changing those tuning parameters. So I hope that kind of makes sense to people, but I would like to try to make the model so that we're not always going after the skewness and club to fix things, because I think that that's changing our ECS. And I don't, that's a very uncomfortable idea to me.
So maybe if I could just ask a quick follow-up, Adam. I think you're totally right. This is a great point that you made. But do we just freeze club gamma at some random value that gives us a certain ECS? Or do you have a more clever way of choosing what the appropriate values are?
I think we're careful when we do the tuning to not take it out of bounds. Mm-hmm. But, you know, that's just what we do in the back room among us. You know, what other buildings related to NCAR do, you know, they may just feel like this is the new RH min parameter and go at it. So, yeah, I just, I'm sort of hoping that by implementing MFs with their additional level of skewness into the solution, that we have another way of controlling the shortwave cloud forcing, not by tuning gamma, but by introducing a process that produces a more realistic trade cumulus.
Okay, yeah. Yeah, so Andrew?
Yeah, so maybe I'll interject a few other things related to this that haven't been mentioned. I think along the lines of what Adam said, it's not just, I mean, it's not just feedbacks, but as Adam said, or the TOA, but our mean state of stratocumulus clouds could certainly be improved. And I think the things that Ben and also with the club MF that Adam talked about and what he was just saying about introducing skewness are good there. And I do think we are, as I said, doing some work on mixed phase ice microphysics. On the aerosol forcing side, which is probably also on the high range of what's been observed, and we see reactions to things like liquid water path in the model that are an emergent property that doesn't look that well supported by observations. I think there's a number of different elements, both on that's sort of working on a mean state bias there, looking at both rain formation in the microphysics. We've done some work on machine learning that's improving that. And I think we'll continue to do that. And then the coupling of turbulence in the microphysics, which will relate to things like evaporation and actually seeing that work better is something process-wise I think that's important to work on. And this gets into, I guess the last point I wanted to make is the other aspect of this is physics improvements for new science. The second sort of point I made, and that's, I think, better parameterizations that work better across scales. So for the microphysics, we've been moving in this direction for a while, which is to try to work all the way from the small scale, the mesoscale, or even the LES scale, all the way up to the climate scale. So we've added Groppel and Hale, Rind ice in there. We're moving towards sort of a P3-like unified ice in the microphysics. We're adapting the code for GPUs. And then I think the other thing is harmonizing how the microphysics works with the turbulence, and that means the shallow and deep turbulence. Some of that's what I just mentioned about for aerosol purposes. The other is, has been said, getting some sort of deep coherent turbulence that's going to work across scales. So dealing with the deep convection as we go from 4 kilometers to 12 kilometers to 25 kilometers to 100 kilometers. And you know, the hope has always been the club, or so now some combination of club MF could get us there, maybe with these modifications to club that are being worked on. So I think, you know, that doesn't give us very much to do in the next couple of years. So, but I think there's a lot of exciting science there, right? I mean, that's where I would sort of say I'm excited about all these things. And I think it has relevance both for biases, emergent property changes like ECS, as well as process improvement and mean state improvement.
Great.
That's a bit of a laundry list, but I figured I'd throw it out there and see if people had reactions to that. And I probably missed some stuff on gravity waves and some other aspects of momentum. Momentum is another one.
Mm-hmm. Okay. Any other reactions, particularly from people we haven't heard from yet? Don't be shy. They're shy. Okay.
I have a different question.
Okay.
I don't know if this is the right time to introduce this topic, but I'm just wondering about sort of schedule and timing. Like, at what point can we start breaking the model? At what point can we introduce a new improvement that requires retuning? You know, so we have some things in club that are kind of on the shelf, and we could try and turn them on, but I don't know what stage we're at in terms of, you know, retuning the model, introducing new changes to the formulation.
Yeah, that's a great question. I guess maybe getting at timing in general. So I think that Kevin kind of asked a similar or related question earlier today about, well, what's the timing for model improvements getting into CAM-7? And Julio gave one answer, which was, you know, well, the CPTs are something like 3 to 5 year projects. So that's kind of one time scale. But I think another time scale that someone else probably knows off the top of their head, but I don't, is there actually a freeze date for CAM-7 or a freeze year? Do we know? And then I guess beyond that, to directly answer your question, Vince, I guess my feeling is that making sure that people know of the improvements that you have on the shelf that are ready to go is important, regardless of when the tuning actually happens, which probably won't be for several years. So does anyone have a better answer to that?
I mean, the model, I think, can be unfrozen in the sense, I would encourage us to break it incrementally as we go forward and not have to just say, we're CAM-6, and then we're going to pile up a whole bunch of things and try to throw them together at the end. I think we make our best shot at a model moving forward. We add improvements as we go, and we try to make sure we can at least get a reasonable mean state climate. And I don't know. I mean, there's a bunch of options here, but I think, you know, some of this we're going to move forward on a SEMA perspective to try to pull together a lot of these physics changes that can work across scales and that other people are going to want. And that's going to develop maybe along a slightly different path than how CSM and the AMWG want to actually codify whatever CAM-7 configuration exactly goes forward. So part of SEMA is going to enable some more of this experimentation. Part of the Common Community Physics package should enable on the physics side things to be more easy to put in things that are more interoperable and switch them in and out potentially. But that's up to, you know, Julio and Peter and others, Christian, to figure out exactly how we govern an official version and how close to fidelity we need to stay at all times in the development process.
I would also add, I mean, I'm just going to say, my own feeling is that the time to break the model is now. I mean, we're already breaking it in many ways. You know, we're talking about a new DICOR, we're talking about new vertical resolution. There's a new ocean model. So there's a lot of things, you know, the CAM-6 CSM2 is dead or broken, or I don't know what, no, it's frozen and we're moving on. I think the time for making changes in the model is now. So I think, Vince, we should talk to you about all the things you want to put in and you know, start getting them in.
Okay. I mean, the challenge is always retuning. So would that be,
yeah,
like UWM would just take a shot at the tuning? Or, I mean, does it need to be tuned in coupled at ocean atmosphere mode at this point, or?
Well, I mean,
take a shot at it. Let us know what you did and we'll help. I mean, we're going to, you know, microphysics, we have some changes that are going to require retuning too. So the other thing is I should note, and Trude Eidhammer is going to talk about this tomorrow, we're developing a perturbed parameter ensemble methodology that can be used to help us understand the sensitivities of parameters that hopefully can be used for tuning, both for CAM-6, and it should be easy to replicate for CAM-6.x, whatever that is. So if you introduce new parameters or we put in new parameterizations, we can actually look at their sensitivities in a more objective way that should enable us to get a better understanding of what the sensitivities are of individual and collective parameterizations going forward, rather than the optimized random walk approach that we've been doing.
Yeah, that could be very helpful.
I mean, this is Rich. It is worth thinking about this a lot, because if past his prologue, you know, CAM-5 and CAM-6 were not pretty. There's no doubt about it. The way we went from point A to B, where B was a CMIP6 model, we did not plan it that way. So I think it may be worthwhile thinking about what we did back then and what we could do differently, I think.
Mm-hmm. So is your concern that as we break the model, we do not break it so much, or are you thinking there ought to be parameters placed on how far we stray from?
Yes.
Okay.
I think we need some parametric kind of understanding of how much are we willing to bear in terms of a number of things that go into the model in one go, then to retune.
Yeah.
It can't be everything, which was, in the end, was CAM-5.
I think the PPE approach can provide some frameworks on that, because the PPE is designed to be run for any model comp set we want. You can run single column models. You could run a 2-degree model. You could run 1 degree. F cases, you could run it all the way to coupled. So there's a lot of different opportunities to help get, I think, that parametric understanding, which I agree, Rich, would be very valuable in looking at individual or collective parameterizations, as you said.
And that talk on PPE will be at 3 p.m. tomorrow. Or sorry, 3 p.m. Wednesday.
Great. Looks like Tomas has his hand up. Tomas?
Yeah, just briefly, I find this conversation extremely interesting because when I think about it, to me, it's obvious that CAM has no real weakness, because there is so much development happening on its back that really a lot of what is done in CAM is actually fairly well controlled on. But I see the change in vertical resolution as quite a major step. And to me, it seems this should be done maybe before additional developments. It can be quite difficult to attribute, to go back and understand what happened if you change, as Rich was saying, essentially too many things at a time, and in particular, changing the dynamics, the discretization, and the physics at the same time. Past experience at the Met Office has shown that it can result in a bad model, because it becomes impossible to tune. This was the experience with WACCM. So where they did exactly that. They changed everything at the same time. So it's a good idea to do one category, at least at the time. You can change a lot of physics, but not also as you change the discretization and the dynamics, because then you don't know anymore what's happening.
Mm-hmm. Yeah, so are we talking also about, I would call it code revision system? I mean, are we, we can't, we're not saying people shouldn't be developing physics in parallel with the changes to the vertical resolution. We are talking about the timing of introducing these things into the model. And I don't know, maybe we need to talk about.
I agree with you there, Julio. I agree. Now is the time. I agree with that, definitely.
How many branches, how many development branches at a time can we support? Is that a question we need to think about?
I think we can support, or should be possible to support a number of branches, but I agree with Rich and Tomas that it would be nice to have, to maintain this principle of revertibility, like to be able to undo a change or go back to prior versions and see the effects. We did that a bit with CAM-6, reverting to version 1.2.5 and so on. But that should be possible if the commits are made sort of one at a time. Commit the microphysics changes, club changes, vertical grid changes, and so on.
I see Steve's on the call. That's what we do. I mean, we're very. I think the commits are very incremental. A die core commit and then nameless change commit. I think we do that already. So that's good.
Rather than trying to say we're supporting a lot of branches, I think the right terminology is we support a lot of configurations. And there's no reason not to have parallel configuration development going on. The question in my mind is which configurations are going to get a lot of simulation time so that we can see how it's doing.
Yeah, I think Steve is exactly right. I was going to say that I think that everyone does development on their own branches. The more, the better. I think the real question that we've been kind of asking here is, do we just have a ton of branches that we all just try to merge all at the same time and do one tuning exercise at the end, or do we do incremental tuning exercises? So we have like a CAM 6.1, CAM 6.2, and maybe each one has just, maybe 6.1 is higher vertical resolution and CAM 6.2 are the ideas that Vince is adding on top of the vertical resolution and so on like that, which might end up leaving some people stuck tuning for the next 10 years all the time. But it certainly is more reversible in terms of figuring out what each change did.
I think we also have to, maybe make some assessments of changes, whether the changes that everybody, whether they're changes that are going to be the foundation for other changes or whether they're relatively kind of orthogonal. I mean, vertical resolution is a great example of a change I think has to go in. I agree with Thomas. This is a change that has to go in before we get too carried away with other things.
Okay, it seems like we have a pause in the conversation here, and I'd really like Hong Li to be able to finish his talk. So maybe everyone think about further discussion items while Hong Li finishes, and we can talk more later.
And we'll also have another cloud physics type discussion tomorrow. So,
Hong Li, do you want to take it away?
Yeah, sure. Okay. Yeah, let's see. I think I got stopped here last time. So
that looks right. Yeah.
Okay. Yeah. Yeah. So what I showed here is basically the simulation, the zonal mean surface air temperature difference for a couple of different set of simulations. So if you look at the red curve, that's the difference between scattering and the non-scattering. And you can see the difference is largest over the Antarctic, over the Arctic in the DJF. And another set of simulation is this yellow curve. So the yellow curve is we turned on scattering everywhere except the far infrared part, which we mentioned. So just within here, we turn off the scattering. For all the other part, we still maintain the scattering. And that is just try to highlight how much is the importance of scattering in that portion of spectrum, which is the far infrared. And you can see if we turn off just that two-band scattering, then there's no much difference from this fixed SIST run. And so that highlight this difference between the red and the yellow is due to the far infrared scattering, not from the mid-infrared. And if we look the plot in the JJA, you will see similar situation, but now the largest change is in the Antarctic rather than in the Arctic. So the physical interpretation of this one is straightforward. So when you turn on the scattering, the photon, which otherwise will go to space, now have a chance to be scattered around. But remember, that's in the water vapor band. So when the photon scattered around, it has chance to be further absorbed by the atmosphere. So in another word, when you turn on the scattering, effectively, you increase the greenhouse efficiency of additional greenhouse effect by this ice cloud. And this additional greenhouse effect is much more prominent in the high latitude over the winter rather than in the actual polar region. And that's the reason you get the largest increase in the polar winter. Okay? And so just we actually also did some tests to see what's the impact when we include both the surface emissivity and the scattering. So in this slab ocean setup, the two effect is largely editable to each other. And both actually has this latitudinal dependence and more prominent over the polar region than in the mid-latitude and the tropics. So we just show when we combine them together, which is this yellow curve, which can be largely approximated by just a summation of the blue curve and the red curve there. So there are more analysis in our paper talk about the impact on the radiation budget at both surface and the top of atmosphere. Basically, it has no impact at the TOA energy balance, and the impact on the surface energy is much more prominent over the winter than summertime. So just to sum up, there are, in our argument, there are two missing long wave physics in majority of GCMs, the long wave scattering and the surface spectral emissivity. And we have the treatment for both of them. And we think there's a well-rounded physical argument. They are much more important than the polar region, than the actual polar region. And it matters much more for the surface energy budget rather than the TOA. And the other thing is actually among those scatterings, the far infrared is actually the most important part. And it's actually also the spectral region. As of today, we still have no spectrally resolved observation from space yet. Okay? And that actually will be changed in the incoming decades. And globally, when you enable this long wave scattering, it's actually increased the downward long wave flux at the surface by about 2 watts per square meter. So that's actually a not a small perturbation, even you look the global average there. So I think I will stop here. Here I just list some reference and the code URL there. So thank you. Yeah, sorry about the technical hiccup there. So.
All right. Thanks. That's very nice as usual. So does anyone have any questions then for Hong Li? I don't think so. I think everyone is they took me seriously about the keep thinking about the discussion. So, okay, thanks a lot. I guess let's return to the discussion for a couple of minutes. This discussion is supposed to be 30 minutes to 45. We have another 10 minutes before it'll be 45 minutes, in which case I say that we should probably, at that point, I think we should just cut off and continue the discussion tomorrow. Does anyone have any comments, either for Hong Li or for about the discussion that we were having before? Any other physics items you want to bring up? So I guess I will say that I think that Rich brought up an interesting idea of, on the chat, of doing a tuning every 6 months, with the idea of if you get your changes in by that time, they get tuned. If not, you have to wait another 6 months. Is a good way of kind of having things be more incremental rather than an emergency all at the end.
Yeah, can I just, I mean, sorry. Now, my thought is, I was just thinking, it's like, just one more thing. Let's just do one more, wait another week for one more thing. And I'm feeling that if you make that interval short enough, it doesn't seem so bad that you missed it. That you can, you make a good effort then to make the next 6 months or 4 months or 9 months, whatever. I just think you really want to avoid that. Just one more thing, and everyone's waiting for this one person who, we think it's really important, but then everyone's like backed up waiting. And then it's just a certain kind of, in my experience, a certain kind of desperation that takes over.
Yeah, I like the idea. I guess it's just a problem of finding the optimal interval.
Right. And I think also the people that would be in charge of doing that 6 monthly or annual tuning as well. Okay. Any final ideas, comments people want to bring up before we sign off for the day? Okay, sounds good. So I think that if I'm correct, we start tomorrow at 10:30 a.m. With the DICOR discussion.
Well, 9:30.
Oh, sorry.
Mountain time, Boulder time.
Yeah, I was giving Pacific time, only I gave it backwards, and it was also wrong there. So yes, 9:30 Mountain time. Thanks for the quick correction. So, okay, talk to y'all later then.
All right, thanks.
Thanks all, that's good.
Bye-bye.
See you. Thanks everyone, bye-bye.